next speaker on water purification, Nikita Yadav, Environmental Nanotechnology, Amity School of Earth and Environmental Science, Amity University, Haryana. Nikita? Hello? So it seems to be Nikita is also absent. Then we can go for the next section, biomedical application. Uh, Let me invite L. Karthikeyan, Bio-Nanotherapeutics Research Laboratory, Cancer Research Program, School of Life Science, Bharatiya University, Coimbatore. Karthikeyan?
Yes, sir. I share my screen.
Okay, fine. Karthikeyan, is there any problem?
Yes, sir. The system is lagging, sir. 1 minute, sir, please.
Oh, okay, fine.
Sir, my slide is visible, sir.
No. It's not visible.
Sir, now.
No, Karthikeyan. Yes, it's coming. Fine.
Okay, sir. Okay.
Can you put it in full screen mode?
Yes, sir. Yes, sir. Okay, full screen, sir. Visible.
Yes,
Sir,
very good.
Okay, sir. Okay. Good evening to one and all. I'm Karthikeyan, Department of Zoology, Bharatiya University, Coimbatore. I present my topic and intelligent photothermal nanothermostic treatment of targeted tumor cell ablation induced immune system activation for immunotherapy of cancer. Cancer is one of major health hazards in worldwide. There are more treatment options in cancer or surgery and chemotherapy and radiation therapy and immunotherapy. We focus the combination of photothermal and immunotherapy. Photothermal therapy, the photothermal response agents, metals and carbon and conjugated polymers, they are response to NR window and 1 and 2 and low power density used for the photothermal therapy. And it's combined to photodynamic and chemotherapy and immunotherapy. We combine to photothermal immunotherapy. The photothermal therapy and induce the ICD of immunogenic cell death in the tumors. The dying tumors are release CRT and ATP, HMGB1. They are released and it's mature the immature dendritic cells to mature dendritic cells. And the mature DCS proliferate the T cells and it's released the INF and some immunokines and they directly suppress the remaining tumors and lysis the cells and used to reoccurrence of tumors. And cancer theranostics, the cancer theranostics have received immersible attention and emerging solution for cancer therapy and diagnostics. Several biocompatible photothermal agents developed for the photothermal therapy of cancer. Polypyrrole is PPY is an organic conjugated polymer used for photothermal and photoacoustic imaging. And TAT peptide, it is used to nuclear targeted ablation. And hyaluronic acid used for CD44 overexpressed tumor cells. And resicumab is it is a TLR7 and TLR8 diagnostic used for the immunotherapeutic, and it increased the DC maturation of tumors. And our objective, we developed to design a nuclear targeted NAR responsive photothermal therapeutic agent that actively targeted for CD44 receptor overexpressed cervical tumors. And our focus is NAR2 window, the PPI developed by the NAR2 light source, and it used to control the irradiation focal tumors and different depth and normal cell, unaffected to the normal cells. And we promote the targeted effect of photothermal immunotherapy, which combines photothermal and immunotherapy. It is a promising strategy to overcome the limits of PTT and anti-cancer efficiency. It is our proposed mechanism of our nanocomposite of PPY and TAT and HA and R848. We synthesize the APS polymerization, and our nanocomposite inject to the tumor mice and expose the NAR to 1064 laser irradiation. The laser irradiation, the mechanism, our nanocomposite entered to receptor mediated CD44 receptor mediated endocytosis, and it's released the R848, and it's entered to the PPI TAT and nucleus of tumors. And irradiation time at the 1064 nanometer, this PPI PPI material expose the temperature in the tumors. The temperature above 45 degree, the tumor cells are not survivable in the tumors, so the tumor cells are ablate. Also, the R8 for also the dying tumors are release the HMGB1, CRT, and ATP, and it's these all are early activate the immature DC to mature DC. And also we use to R848. They are also dually act to the DC maturation, and they used to T cell and CD8 and CD4 develop, and the CD8 and the CD4 used to tumor regress and metastatic inhibition. This result and discussion. Our nanocomposite of PPI, TAT, and HAR848, it is UV with NAR absorption in the NAR2 window of 1064 nanometer, and the TEMI may show the it is less than 6 nanometer in size, and it is the UV of different concentration of our nanocomposite. They are expose the concentration dependent absorptions, and it is Xrd pattern of our nanocomposite is a polymeric backbone, and it is XPS data to analyze the our nanocomposite and of polyaniline conformation, and the FTR data of our nanocomposite of HAR848 and PPA, all the materials incorporated in our nanocomposite, and the TGA studies to evaluate the thermal stability of nanocomposite. In the above 600, it is less than 60% to stability, reduce the stability. And it is photothermal properties and photostability of nanocomposite. Our nanocomposite exposed to NAR1 and NAR2 window. NAR1 the 808 nanometer, and NAR2 1064 nanometer irradiation. The nanocomposite of time dependent manner, they increase the temperature of 808 and 1064 nanometer. With compared to 808, at the 1064 is higher than the compared to 808. These are temperature concentration dependent manner. The temperature increase the this is 808 and this is 1064 compared to high concentration of 100 μg/ml ml. The increase is 53 degrees Celsius, but 1064 nanometer is increased the around 58 degrees Celsius. This is final temperature curve. and our temperature curve of temperature to stability check the our nanocomposite in the sign in green of FDA approved dye. There after 5 cycle continuous cycle, our nanocomposite of 1064 and 808 exposure, it is stable in the temperature, but the free ICG to after 5 irradiation, it is reduced and unstable in the cycle 5 cycle. It is our photo stability of nanocomposite compared with ICG. It is good photo stability compared with ICG. It is photothermal conversion efficiency and R848 release. The photothermal conversion efficiency of 808 and 1064 nanometer. It is higher than the compared to 808. 1064 nanometer is higher than photothermal conversion efficiency of nanocomposite 40.6%, and it is R848 release. And the tumor microenvironment, it is pH of 5 is high. So our R848 release in the pH of 5 is around 60% compare both NR irradiations. It is stability of irradiation of our nanocomposite to evaluate the UV. Before and after irradiation, our nanocomposite is stable, but compared to the ICG, the before irradiation of ICG peak is 800 nanometer, to after irradiation it is decreased. So nanocomposite is good stable to NR light. And it is in vitro biocompatibility and targeted photothermal ablation of cancer cells. We choose CD44 positive HeLa cells and CD44 negative NIH3T3 cells. After biocompatibility, the cell viability of without laser and compared to 808 and 1064 nanometer laser, and the CD44 positive cells compared to normal cells, it is very decreased, and CD44 negative cells are cell viabilities compared to CD44 positive, there is high. Because of CD44 negative cells, we used to HA targeted, so it is decrease in the nature. And it is a LDH release. We evaluate the LDH for our nanocomposite to any damages in cell membrane. That high concentration 100 mg by ml, there is very less than LDH release in the treatment groups. And it is HeLa cells of fluorescent imaging, calcium AMP staining used to control, and nanocomposite and nanocomposite plus 1064 nanometer NR laser. Our nanocomposite and control groups are live cells are showing, and the NC plus 1064 nanometer NR group to ablate the cancer cells to its response to the nanocomposite plus laser.
Cut again,
Sir,
please conclude.
Okay, sir. This is hemolysis assay, and it is used to biocompatibility, and photoacoustic signaling is refers to photoacoustic imaging property of our nanocomposite, and it is in vivo tumor growth. The tumor volume reduced by the nanocomposite plates NR group, and this is the animal tumor imaging of our treatment group for NC plus NR. The tumor area is high temperature occur, and tumor area temperature around 58 degrees Celsius. And our treatment groups are showing average body weight is not no significant compared to other groups, and it is urine examined for our nanocomposite biocompatibility. After collection treatment group, the excretion of urine to confirm the our nanocomposite to excrete the via urine. The histopathology, no organ damages show. And the immunogenic cell death and the immune system activation assay of ATP and CRT, HMGP1 and DC maturation, T cells.
Again, your time is exceeded.
Okay, sir. Okay, we conclude that our nanocomposite to activate CD44 receptor overexpressed cancer, and it high biocompatible used for photothermal and immunotherapy. I sincerely thank my guide, Dr. Vivek, and concerned support of Bardiyar University. Thank you.
Okay, now the session is open for questions. Anyone? So if there is no more question, we can go for the next presenter. Thank you, Karthikeyan.
Thank you, sir.
Thank you. Okay, wait. So now let me invite Danyashri M, Department of Pediatric and Preventive Dentistry, Faculty of Dental Sciences, MS Ramaya University of Applied Sciences, Bangalore. Welcome, Danya.
Good evening, sir.
Good evening.
Can I start with my presentation, sir?
Sure. Just share.
Is it visible, sir?
No, it is not visible.
Now is it visible, sir?
Yeah, it is visible. It is visible. Please put in full screen mode.
Is it fine, sir?
Not yet. It is. Did you share the just slide or the entire screen?
Entire screen, sir.
Actually, it's a Google Slides.
No, sir. Now it's visible.
It is visible, but not in slideshow mode. It's fine. You can continue.
Okay, sir. So, good evening to one and all present here. So, the topic for today's topic is, are nanoparticles the future of dentistry? So coming on to the introduction, so basically nanoscience and nanotechnology, it is the study and application of extremely small things, and it can be used across all the other science fields such as chemistry, biology, physics, material science, engineering, medicine, and dentistry. Physicist Richard Feynman is regarded as the father of nanoscience and nanotechnology. In India, Professor C.N. Rao is regarded as the father of nanoscience and nanotechnology. So coming on to what is dental caries. So dental caries, we commonly address it as tooth decay, which is a grave public health disease, and it remains the second most common disease in human civilization after common cold. It is also the most prevalent condition included in the 2017 Global Burden of Disease study. If your eyes are the window to your soul, then your mouth is the mirror of your health. Although this idea may seem far-fetched, health experts believe that good oral health care does more than prevent tooth decay. So basically, when does this tooth decay develop is when the bacteria in the mouth metabolizes the sugars to produce acid that demineralizes the hard tissues of the teeth. As you can see in this image, this is the hard tissue, that is the enamel and dentin. So almost half of the world's population is affected by dental caries, making it the most prevalent of all health conditions. So according to the studies conducted in developing countries like in India, the incidence rate of dental caries among 13 to 19 years old is 36.7%, while it is as high as 83% among 6 to 8-year-old children. So as you can see, this is how the dental caries look like. So in most cases, whenever the decay has progressed beyond the earliest stage, the treatment requires removing the decayed part of the tooth and replacing it with a filling material. As you can see, we'll remove this decay and we'll use a filling material. So these fillings are nothing but these are the materials placed in the teeth to repair the damage caused by the tooth decay, and we call that as restorations. So the most commonly used restoration in dentistry is glass ionomer cement. This is that glass ionomer cement. So this glass ionomer cement has a radiopaque glass powder and an organic polymer liquid. So it offers a strong adhesion to enamel and dentin, and it also possesses high compressive strength. Apart from that, it also exhibits certain favorable characteristics such as chemical bonding to the tooth structure, translucency, like it gives the tooth white color appearance. After removing this, it gives the tooth colored appearance, and fluoride release. Despite its anti-cariogenic effect, the most common cause of failure rate of this glass ionomer cement is the secondary decay. So several studies have been done to enhance the antibacterial property of this glass ionomer cement. So secondary caries is nothing but after restoration, you can see this black is discoloration again. So this is called as secondary caries. So to enhance this property, several studies have been done, and several nanoparticles have been incorporated into this GIC. So let's first look into what are the drawbacks of those nanoparticles. So first is zinc oxide nanoparticle. It did not promote any antibacterial activity against the Streptococcus mutans, which is the bacteria responsible for the dental caries. Next is the silver nanoparticles. So it caused discoloration of the material that comes in contact with it. Next is the magnesium oxide nanoparticle. So changing its nano properties into micro ones, its application in dental materials is adversely affected. So now it's definitely a time for a change. So we thought we'll take the cerium oxide nanoparticles, which have gained much attention recently in the context of biomedical application due to its unique antibacterial activity against both gram-positive and gram-negative bacteria. Apart from that, it also exhibits potent properties such as anti-tumor, anti-inflammatory, and antibacterial activities. So green synthesis is replacing our chemical synthesis with the nature's recipe book. So we thought we'll prepare the cerium oxide with a green synthesis method. So we took this edible mushroom extract. So how we prepare this mushroom extract is, so first these mushrooms were cut into small pieces. It was washed several times with deionized distilled water. After that, 25 grams of this cut mushrooms were mixed with 125 ml of distilled water, and it was stirred at 60 degrees Celsius for 15 minutes. Then this filtrate, it was refrigerated at room temperature until further use, and it was used as a reduction agent and stabilizer for synthesis of cerium oxide nanoparticles. Coming on to the biosynthesis of cerium oxide nanoparticle preparation using edible mushroom extract. So a total of 3.72 gram of cerium nitrate hexahydrate was added in 50 ml of edible mushroom extract. Then that solution was stirred using magnetic stirrer at 80 degrees Celsius for 2 hours. As you can see, there is a formation of light brown precipitate is observed. After that, the resulting solid was calcined at 600 degrees Celsius for 2 hours to obtain the cerium oxide nanoparticles. Now we have obtained the cerium oxide nanoparticles from the mushroom extract, as you can see in this picture. Now we'll incorporate this biosynthesized cerium oxide nanoparticle into GIC. So the steps followed for this study was the microorganism for the antimicrobial analysis were purchased from the microbial type culture collection and gene bank Chandigarh, and the bacterial strains were maintained on the nutrient agar. So the pure cultures from the plate were inoculated into nutrient agar plate, and it was subcultured at 37 degrees Celsius for 24 hours. A standardized inoculum was used for this antimicrobial test. So coming on to the results, first we got this FTIR analysis. So in this FTIR analysis, the FTIR peak is confirming the successful reduction and stabilization potential of mushroom extract for the formation of cerium oxide nanoparticles. SEM analysis, first image shows the SEM analysis of glass ionomer cement. Second, it is being clearly reflected from that second image that uniformly agglomerated cerium oxide nanoparticles were successfully formed after incorporation into GIC. Coming on to the Xrd results, so the strong and sharp diffraction peaks indicated the good crystallinity of the cerium oxide nanoparticles. Then we went about the antimicrobial testing. So the methodology what we followed was, so the medium was first prepared by dissolving 38 gram of Muller-Hinton agar medium in 1000 ml of distilled water. Then the autoclaved medium was cooled, mixed and poured Petri plates, and the plates were swabbed with pathogenic bacteria culture given samples of 1 milligram per ml concentration. Then 3 walls of 6 mm were bored in the inoculated media with the help of sterile cork borer. Finally, the sample-loaded discs 1 milligram per ml were then placed on the surface of this medium, and the plates were kept for incubation at 37 degrees Celsius for 24 hours. At the end of the incubation, the inhibition zones were examined around the disc, and it was measured with a transparent scale in millimeters. So the size of the zone inhibition was measured in millimeters. Then the absence of zone inhibition was interpreted as the absence of activity, and the activities are expressed as resistant if the zone of inhibition was less than 7 mm, intermediate and sensitive if it was more than 11 mm. So here we use streptomycin as a standard control. So as you can see in the results, so antibacterial activity of the given sample in 3 dilution against one bacterial strain, that is Streptococcus mutant, it was in comparison of positive control, which was streptomycin, and negative control. So we found, as you can see from the result, we found that Cerium oxide incorporated into GIC had an effective antibacterial activity. So coming on to the discussion, so the antibacterial mechanism of Cerium oxide nanoparticles. So first, the positively charged nanoparticles were adsorbed onto the membrane of negatively charged gram-positive and gram-negative bacteria through electrostatic interaction. Second, Cerium oxide nanoparticles could attack proteins after absorbing on the outer membrane of the bacterial cell. Third was the oxidative stress. Fourth, it induced hydrolysis of a DNA oligomer into the fragments, which then could be successfully manipulated by natural enzymes. So our study showed a good inhibition against Streptococcus mutants, which was a desirable result. So apart from this, the added advantage of Cerium oxide is that it has a property of disrupting the biofilm by interfering with the adherence of bacteria. So conclusion is, from the results of the study, we found that the Cerium oxide, that is biosynthesized Cerium oxide infused into GIC, showed a good antibacterial activity, which was comparable to the positive control, that is streptomycin. So this provides a gateway to explore the further properties of Cerium oxide nanoparticles and conjugate it with dental materials to enhance the antibacterial activity. So the impact of the nanomaterials is expected to exceed the impact that the electronics revolution has had on our lives. So these are my references. And thank you.
So the session is open for questions. Okay, if there is any no more questions, thank you, Dhanashri,
Thank you,
for the
sir.
presentation.
Thank you, sir.
So let me invite Ramanjit Gao, Department of Physics, Punjab University,
Yes,
Chandigarh,
sir.
India, for the
Yes,
next
sir.
presentation. Okay, you can share your slides.
Sir, is it visible?
Yes, it is visible.
Okay. Good afternoon, everyone. Today I am going to present my topic called nanoparticle synthesis using chemical and green method and their cytotoxicity against the cancer cell lines. So these are the outlines for my today's presentation. So let's start with the introduction. The term nano originated from the Greek nanos, which means draft. It is 1 millionth of meter. Nanotechnology is the field of applied science and technology whose aim is to control the size of matter and the fabrication of device or material on the atomic and molecular scale, generally between 1 to 100 nanometer. Among nanomaterials, metal and metal oxide based nanoparticles shows interesting biological, optical, magnetic, catalytic properties that in general related to the shape and size. So an increasingly application is the use of metal nanoparticle for antimicrobial, antibacterial, antifungal, and anti-cancer and biomedical devices. Now the cancer is abnormal type of tissue growth in which cells exhibit an uncontrolled division relatively in autonomous fashion, leading to the progressive increase in dividing the cells. There are various kinds of cancer like carcinoma, sarcoma, and lymphedema and leukemia. Despite of aggressive efforts, breast cancer treated is still limited to the classical radiotherapy and chemotherapies. The majority of recent trends has been against in the research related to the study of anti-cancer activity using nanoparticles. Now, nanoparticles, due to their unique physicochemical properties and functional properties, they are receiving a great attention to their chemotherapeutic potential. They offer, unlike classical therapies, which have issues with chemotherapy resistance developed by the cancer cells. Now, increasing therapeutic potential could be achieved very easily due to the affordable and inexpensive method of synthesizing them in green and chemical ways, offering a desired property such as their small size, chemical composition, rendering the biocompatibility for surrounding tissue and toxic to the cancer cells, structures, and larger surface area. Now I have a synthesized methods. First of all, we have using a chemical method to synthesize a PVP capped gold nanoparticle. For this, we have firstly prepared a 1 millimolar gold solution and put on a hot magnetic stirrer. Then we add 2 millimolar solution and continue stirring. The color of the solution changes to red wine, which indicate the formation of gold nanoparticle. Then we add 100 microliter of PVP to the solution to prevent the aggregation of nanoparticles. Then we synthesize the green nanoparticle using green method. So for green method, we have collected the lychee leaf from the botanical garden, Punjab University, Chandigarh. Then we clean it with DI water and crush in a powder form. Then we have taken 3 gram of crushed powder in a 50 ml of DI water, boil it for 30 minutes. Then we filter it with wetman paper 4 and store it for further use for experimentation. Now, with the use of these lychee leaf extract, we synthesize the gold nanoparticle. We have taken a 1 millimolar solution of gold salt, then we placed on a magnetic stirrer. Then we add only 15 microliter of lychee leaf in above solution to reduce the gold ion into gold nanoparticles. The color of the solution changes to red wine, which indicates the formation of gold nanoparticle. Here, the lychee leaf extract act as both reducing as well as capping agent for the nanoparticles. Further result and discussion. First of all, we have characterized the synthesized nanoparticle using UV visible spectroscopy in the range of 300 to 800 nanometers. The most of noble metals like silver and gold considered as a free electron system. When electromagnetic wave interact with the conduction electrons termed as plasma. So the surface plasma resonance was observed in the visible region for 540 nanometer for PVP capped nanoparticles and 536 for leaf gold nanoparticle synthesized by leaf extract. Then we characterize for the X-ray diffraction. X-ray diffraction used to identify the crystalline size of synthesized gold nanoparticle. From the figure, we can see the intense peak corresponding to the Bragg refraction 111 and 200, 220 and 311 set of lattice were found to be based on the phase center cubic. Now, the Bragg reflection is a good agreement with the JCPD card number 040784. Using Debye-Sharare formula, we have calculated the crystalline size. The crystalline size for the PVP capped gold nanoparticle is 21 nanometer, and for leaf extract gold nanoparticle, it is around 14 nanometer. Now, dynamic light scattering. Dynamic light scattering is used to measure the fluctuation intensity of scattered light, which is caused by the movement of the particles. So DLS used to find out the hydrodynamic size of the particles. From this, we have calculated the average hydrodynamic size for gold PVP capped gold nanoparticle is 43 nanometer, and for leaf extract gold nanoparticle is 70 nanometer. Then further, we use the synthesized gold nanoparticle to find the cytotoxicity of against the breast cancer cell lines. First of all, we have cultured the breast cancer cell lines in Eagle MEM and maintain at 37 degrees Celsius in humidity of 5% of CO2 and 10% FBS solution. Then we find the structural changes using phase contract microscopy. We have used 40 microliter of the gold nanoparticles against the MCF7 cell line, breast cancer cell lines. Then we have studied the structural changes by microscopy. The structural changes were recorded acquiring the optical images. We can see from the images the gold, this is the control, and this is image for treated MCF cell lines with the PVP capped gold nanoparticle, and this is the picture for leaf extract gold nanoparticles. The observable structure changes including cellular shape, cell aggregation, cytoplasma condensation, and decreased cell number after treated with the gold nanoparticles. So next, apoptotic activity. In apoptotic activity, after treatment, the MCF cell line with the 40 microliter of gold nanoparticle, we further use stain ethylene bromide and acridine orange to evaluate the DNA damage. For this, we have used fluorescence microscopy to assess the apoptotic activity. From figure we can see this is the control, and this figure indicates the PVP treated MCF cell lines, and this is gold leaf extract and gold nanoparticle treated cell lines. So from the image we can see the fact of DNA damage. The fact that the nanoparticle treated cell lines stain brightly red due to the ethylene bromide in comparison to the non-treated control. So nanoparticle has show cytotoxic effect against the DNA damage. So for the conclusion in terms of synthesis of nanoparticle using biological component, current is focused on the potential application of biosynthesized nanoparticle is innovative advancement in nanomaterials. A simple one-step method to produce the gold nanoparticle using leaf extract, which act as both reducing as well as capping agent. In case of PVP, capped gold nanoparticle was synthesized using straightforward oxidation reduction process. The effect of nanoparticle on cellular morphology and cytotoxic studies show that these nanoparticles are as uptake the cell and result in cytotoxic effect. These are the references. And thank you.
Hello, is there any questions?
Yes, let me check.
If there are no more questions, then we can move to next session. Thank you, Ramanjit, for your nice presentation. Next is next session is on films, and first presenter is Shiva Lamichani. Hello, Mr. Shiva. Hello, Mr. Shiva. Hello, Mr. Shiva. Hello, Mr. Shiva. Are you able to hear? Hello, Mr. Shiva.
After the next presentation, you can present.
Okay, so we can move to next session, composites.
Okay.
Let me introduce Mr. Abhijit Majumdar. Hello, Mr. Abhijit.
Yes, ma'am. Yes, ma'am.
Okay, please share yours.
Greetings of the day. I am Avijit Majumdar. I am pursuing my BTech degree in Mechanical Engineering from Gargi Memorial Institute of Technology. And our paper's name is Ceramic Nanocomposite in Thermal Shock Resistance and Flame Retardant Application. The paper is created along with my classmate Binoy Mandal and our assistant professor, Mr. Hiranmay Samanta sir. The idea of thermally strong structural ceramic nanocomposite became first proposed through Nihara in 1991. Nihara divided uh, the nanocomposite into three types: intragranular, and nano, and the last one is the nano composite. Let's talk about the ceramic reinforcement. Most ceramic reinforcements are based on oxide, nitrite, borite, and calcite. Uh, it has already been proven to be a suitable reinforcement for installations on brittle material, ceramic matrix. Along those reinforcement, SICK is reinforcement material for relative high module and the low coefficient thermal expansion, low density, excellent hardness, and accessibility in various finishes. Let's talk about the advantages. Local increase in stress level due to the internal stress. Number two is the general and the residual compressive states at the crack tips. Number three is the crack growth in the compressive state zone. Number four is the relative displacement. Displacement is matrix and interface and elements. Number five is the matrix micro crack reading to matrix ruptures, including crack parts, the crack deformations or and all bunchings. Number six is the matrix and the fiber in phase pairings, and number seven is the fiber pairings and the fiber package in the crack tips process zone. Here you can see the different types of CMCs diagrams, and the other side you can see the throttling mechanism is the monolithic ceramics. And here you can see the how the six composites for work as a thermal protecting system. Thank you very much, everyone, and thank you to ICN to give me the opportunity to present our paper over here. And thank you everyone for your valuable time. Thank you very much.
Uh, now, now the session is open for questions. So, if there is no question, we can conclude the session. Thank you, Abhijit.
Thank you, sir.
Thank you, Dr. Lishin, for chairing the session. Next, let's move on to the plenary session. I welcome Dr. Madha Prabhakar Chavan, University of Ostrava, Faculty of Science, Czech Republic, to have the presentation on the topic tuning porosity in carbon monoliths.
Okay, so my screen is visible
No, yeah, it's
now.
Can you please make it? Yes, yes,
It's visible and working, right?
yes, yes.
Okay. First of all, I would like to thank the organizers for giving me opportunity to present my research. So today I will discuss the presentation on the topic carbons, how we can create the porosity and tune the porosity according to the applications in adsorption, in supercapacitor or batteries, and so on. So before presentation, I just in very brief, I will explain where I'm from and what I do the research. So basically, I'm from Czech Republic and from the Ostrava city, which is the third largest city after Prague and Brno. And the city is of coal, iron, and university. So basically, in this city, there are two universities. One with the University of Ostrava, where I work as assistant professor, and other university is the Technical University as VSB. So this our university is founded in 1991, and we have several departments, including almost 10,000 students, and we are with the Faculty of Science. And the Faculty of Science contain different departments. We are basically from the chemistry departments. So we have almost 2,000 students and 150 as academic staff. Out of the Faculty of Science in the Department of Chemistry, we are the smallest department, but we have almost 150 students. There are 4 PhD students, and we are with the 16 academic staff. So basically, in our university, we have the Department of Chemistry, and we offer the bachelor, master, and PhD programs. For the bachelor is for 3 years, master for 2 years, and PhD for 4 years. And several students come to our university in the different programs like Erasmus or CPUS programs. Basically, in our department, there are different research areas from coal science to thermal analysis, different nanomaterials for various applications, electrochemistry, biochemistry. But nowadays the city is of coal, so we have previously the research with the coal science, but now it's a decline as we know that the coal sources getting depleted. So we are now more focusing on the porous materials and the different applications. So this is my group where I work as in the group Carbonious Adsorption Group, which is led by our head of the department, Vasek, and I work here as an assistant professor. So basically in our group, we carry out the preparation of carbons, the synthesis. We study different kinetics of this sol gel process, and we tune the porosity for different application. At the same time, we functionalize the carbon monoliths, as well as we dope the different heteroatoms such as sulfur, phosphor, nitrogen in the carbon matrix to enhance the properties for adsorption and the electrochemical testings. So basically, for such characterization, we have gas absorption apparatus. We carry out the nitrogen adsorption desorption experiment. At the same time, we also studied the gas storage of hydrogen, as well as we also study the CO2 capture. Also, we have the DSC techniques that we generally use as a tool for just quickly estimate the pore sizes, particularly the mesopores, and we call it as thermoporometry. Then we will have the different characterizations related to some surface chemistry analysis, as well as NMR reflexometry. And as I discussed that we are do the several applications. Recently, my group is mainly focused on the adsorption and the electrochemistry application with major focus on the supercapacitor. And the gas adsorption applications, we mainly focus on the CO2 capture and the hydrogen storage. And we have the several cooperations within the Europe and outside the Europe, particularly from France, Germany, Poland, and Slovakia. So coming to the research, so as we know that the carbon is a vital which has several applications, starting from the adsorption for depolluting the water, removal of heavy metal ions, as well as removal of organics like phenol. We also have the different catalysis applications of carbon as a support. We also dope carbon in the carbon matrix. We dope the metal nanoparticles, metal oxide composites, as well as we also dope with the graphene and carbon nanotubes. We also study the electrochemical applications like batteries and supercapacitor. So currently we are studying the supercapacitors application from the carbon monoliths. So why carbon monoliths? Why not the powder or other forms of carbon? So basically the carbon monolith, when we compare with the powder form, it is easy for handling. It has a limited attrition and compared to the powder toxicity. And we can make the monolith with any shape using the mold process. So the next is the carbon monolith. So we have to tune the porosity, and why the porosity is important. So if you see the, for example, like a supercapacitor or double layer capacitor, where the ions in the electrolyte solution get attracted towards the electrode, and for such ions we need to have the porosity that is from macropore to mesopore and micropore. So within the powder samples, it is very easy to tailor the porosity. Like we have mesopore contribution, and that mesopore provide the access for electrolyte ions towards the micropores where active sites are held for the storage properties. So however, within this carbon monolith, it is very difficult because we have to maintain the shape, and at the time we have to apply this monolith for different applications. So in this presentation, I will show how some approaches we can do for tailoring the porosity. So basically we are using the sol gel process of polymer precursors to synthesize the carbon monoliths. Basically we are simply using the resorcinol formaldehyde precursor, which is very commonly used nowadays, and the carbon from the resorcinol formaldehyde shows the different applications in electrode for supercapacitor and batteries, in catalysis and in the thermal insulation, and even in the adsorption of different gas as well as the liquid adsorption. So basically here we are using this sol gel approach. Basically that involves the sol gel transition where the polymerization occurs, and there is a formation of three-dimensional structure within the gel. So this gel constitutes of a solvent like a water and the polymerize a cross-link network within it. So this trap water, we can say, we can remove during the drying, and this polymer skeleton gets carbonized during the pyrolysis process, and we can have the carbon with different forms like monolith or powder or fiber or thin films. Based on the drying, the carbon gel is called aerogel, aerogel, cryogel. Basically, the aerogel is obtained by the supercritical drying, aerogel is obtained by the ambient or vacuum drying, and the cryogel is obtained by the lyophilization, also called as a freeze drying. So basically, in this process, we can tune this precursor chemistry, or we can simply change the catalyst concentration, or we can simply change the diluent ratio to obtain the different rate of reaction, and we can tune the different cross-link density within the gel, and we can tailor the final porous carbon structure. So this is the one way. Second is we can tailor the porous structure by using different solvent removal protocols, and we will see the results how we can, with the different drying, how can we improve the porous structure within the carbon monolith. Thirdly, also what we will also see what's the effect of this pyrolysis or carbonization process. And finally, we also study the activation. So how can, with the activation, how amount of micropores we can induce in the sample so that it can be used for the adsorption or double layer capacitor application. So here we can see with this precursor chemistry, we simply change catalyst concentration or diluent ratio. So basically, if we increase the more concentration of diluent like water or ethanol within the precursor sol, basically there will be the increase in a distance between sol particles, and after carbonization there is a increase in a meso or macropore volume. However, this meso or macropore volume controlling is depend on this concentration, and also the mechanical strength is also determined on these factors. So basically here we just tune the network by using just this R is meant for the resorcinol as a polymer precursor, and C is refer for the catalyst. So we just change this ratio, and we have seen that from lower to higher ratio there is a increase in a pore volume, or we can say the induce in mesoporosity, as we can see from the shift from type 1 to type 4 isotherm. So basically this indicates the mesopore within the sample. So understandably at this low R by C ratio, the network cluster could develop over a smaller space, leading to predominance of micropores. On the other hand, at low catalyst concentration, the gel time, there is a longer gelation time, we can say, and this longer gelation time allowed formation of larger and less network clusters, and during carbonization this network of polymer chain leads to larger pores in the sample. And we can see just from this cyclic voltammetry plot for a double layer capacitor application, with increase in this R by C ratio with improve in mesopores, that results in a higher CV higher current, we can say a higher area within the CV curve, and that gives you a more specific capacitance. This is just because of the tuned mesoporosity in such kind of sample that provides electrolyte a better access towards the micropores, where the most of the surface area held for the charge storage. The second factor, we can see the solvent removal. Basically here we studied 3D techniques, like we studied vacuum drying, ambient drying, and the freeze drying. So the samples we call as a aerogel, ATM gel, and cryogel respectively. So basically when the solvent is removed directly through the evaporation, like this way, so there is a formation of liquid phase and a solid vapor phase interface appears in addition to the solid liquid interface. Now, as the surface tension, that is the surface tension of solid vapor interface is greater than the surface tension of solid liquid interface, the energy of the system increases due to evaporation. Now, in response, the system tries to minimize this energy by flowing the solvent from the interior part of the gel towards the exposed solid. However, the resulting pressure gradient that causes the expulsion of liquid from the gel interior is balanced by the compressive stresses, and these latter stresses lead to the shrinkage of the gel network. So if you see the monoliths after the final form, then it gets the shrinkage after the drying as well as after the carbonization. So this dried gel structure basically is a skeletal phase of polymer network and the white phase together representing a contracted and somewhat distorted form of original wet structure. So the contraction and the distortion vary with the space and time depending on the permeability of wet gel structure. So this contraction and distortion can be reduced by use of a solvent with lower surface tension, or use of a solvent with a contact angle of 90 degree, or we can just simply eliminate the liquid vapor interface. As we can see in the cryogel sample, there is a direct sublimation, so there is avoiding of vapor liquid interface, and we can see from the this different surface area obtained by BT or BJH or T-plot methods, there is an increase in volume in case of cryogel sample, as there is a minimization of vapor liquid interface. And here we can see the DFT pore size distribution, where we can retain the pores particularly from 3.5 to 18 nanometer with the freeze drying. So this is the advantage of freeze drying compared to the vacuum and ambient drying. And when we compare with the vacuum and ambient drying, there is a more loss in pore sizes during the vacuum dried, as there is a quick formation of vapor liquid interface and the pore gets collapsed during the drying process. And we can see the electrochemical performance, the improved mesopores with the improved micropores. Also from this plot we can see there is an increase in the capacitance values for these double layer capacitors. So another factor we can do before drying, we can also do a solvent exchange step. And in the solvent exchange step, basically what happens, we have the water as a solvent, and we can see is the during the drying there is a more change in a water volume compared to other solvents. So we just replace with the t-butanol. So there is a there is a more less volume change after drying. So we can see here in the pore size distribution plot. These pores using this DFT plot. So we have restricted the kernels up to 40 nanometer, and we can see within this 40 nanometer we can retain the pore size of the carbon with this solvent exchange step using t-butanol. Further, we can see the effect of carbonization stage. Basically, we carried out the carbonization from 500 to 900 degree, and we see particularly the pores from the 1 to 2, that is the micropores, get improved up to 700 degrees centigrade. And there is no much change in the mesopore size. Thus, it is basically the cross-link polymer network where the different functional groups present, they get eliminated during this carbonization process. And basically there are some oxygen functionality still remain, as well as the micropore contribution. So such kind of samples we can use directly for liquid adsorption, like heavy metal removal, or organics like phenol removal. And the carbons that obtain at higher temperature, which is looks like a conductive, and this material which is carbonized at 800 and 900, because there is a complete removal, almost complete removal of surface groups. So we can use with this improved conductivity as an electrode material for battery and the supercapacitor or other kind of electrode materials. The other way to improve the micropores is just use of activation. Basically, we know that there are two types of activation. One is the physical and one is the chemical activation. Basically, the physical activation is using a gas gas phase, and we use just CO2 as a source for this activation. And on the other hand, we use the KOH activation as a chemical activation. So basically here we can see that KOH activation is somewhat better compared to this CO2 activation in terms of these pores basically below the 1 nanometer scale. Basically, this KOH activation that involves the K plus ion intercalation, and it also gives the combined effect because there is a carbonate formation, and at higher temperature this carbonate also get converted to the CO2. So this is the combined effect, and you get more micropores in the KOH activation compared with the CO2 activation. On the other side, this CO2 activation is just a surface activation. So in the monolith it is restricted for such samples. On the other hand, this KOH activation, for that you need some powder form, it will be better. But for monolith, you have to do such a physical activation. So there is a restriction of such activation agents. On the other hand, we see these cryogel samples show better results. But the main reason is just that there is a the monolithic form is not retained because the material becomes fragile as there is a more range of meso as well as micropores within the sample, and the sample becomes fragile. So it not be a monolith. So another approach, we are doing the template approach, and basically this template approach is a very popular, and it's the one way to tailor the inner structural arrangements such as the pore size and the overall porosity, along with the outer shape and the size of the samples. This approach is flexible and can be applied with variety of methods for the preparation of materials, including polymers, carbons, metals, and metal oxides. In general, the templatings are broadly categorized into hard template and the soft template. In the former hard template, precursors are filled into the pre-ordered made templates, for example, mesoporous silica or replicated carbon templates, and with heat treatment at elevated temperature like calcination or carbonization, followed by temperature removal through subsequent steps results in a well-ordered meso-macroporous network. However, this approach is a long and complex and requires several steps to make the template itself and further removal of template during the removal stage, which is more cumbersome and often involve the use of hydrochloric acid. In contrast, this soft template approach involves just self-assembly between precursors and the block polymers, like organic polymer template or inorganic organic metal precursor or template, which upon further heat treatment at elevated temperature results in a simultaneous removal of this template, and at the same time, with the removal of template, the pores are created within this carbon monolith. So this soft template approach simplicity in processes, as we can directly use the monolith and the soft template as a source for creating the meso or macropore, depending on the use of the suitable precursor. So here we use the pluronic as a surfactant, which contain the PO, PPO blocks. So basically polyethylene oxides as a hydrophilic and the PPO as a hydrophobic block. So we use a simple process where we use the precursor solution of resorcinol formaldehyde for polymerization, and we use water and ethanol and sodium carbonate as a catalyst, and we simply form a templated gel just by a sol gel approach. Now this gel is dried to remove the solvent like water and ethanol, and the final dried form is get carbonized at 500, and we use the slow pyrolysis to make a monolith. So here we use the different concentrations of the surfactants, and here we can see NT refers to no surfactants, and the STR21 and STR11 represent the double concentrations of soft template related to the resorcinol. So here we can see the shapes during these processes like the gel formation, then the drying and the carbonization. So here we can see there is a good monolith formation with the STR11 sample as compared to 211, 2 by 1. The reason is that the 2-1 it becomes the micelles become throughout the gel network, and they with the larger sizes. So the final form you get the meso macropore size distribution, and the mechanical stability get decreased with this higher concentration of surfactants. So we studied this porous property of such monoliths, and we can see with these three forms. So we deeply investigated this STR11 and the monolith shows the better form. So we carried out the adsorption and the adsorption test from phenol and the methylene blue in the aqueous solution, and we found that this STR11 shows the better performance for phenol and the methylene blue adsorption. So basically with this CO2 adsorption, nitrogen adsorption, desorption, mercury porosimetry, we found this carbon we obtain in the monolithic form is a hierarchical one. Means it has the micro, meso and the macropore connectivity. So this sample we take for further study as STR11 as the ideal sample for further tailoring the porous property. So what we do basically here, we just change from slow pyrolysis to fast pyrolysis. Basically we obtain the monolith from 1 to 2 degrees centigrade per minute of heating rate, and now we are using the fast pyrolysis with 10 Kelvin per minute as a heating rate. So basically we carried out the same process as I explained before in the slide, and here we just change this pore structuring part like a pluronic with some modifications using the concentrations for fast pyrolysis process, as well as the use of non-polar solvent like benzene, toluene or cyclohexane, different surfactants apart from the F127, other pluronic surfactants, as well as the mixed forms, as well as we also incorporated some ionic strength for to study the interaction between the non-polar solvents and the template source. We also change the catalyst concentration, and these several parameters we are studied to how this porosity gets tuned in such kind of hierarchical network. So here we can see with this pluronic, as we see in the previous that STR21 sample, even in the slow pyrolysis, and now these results are a fast pyrolysis, we can see that these samples show the bigger pores compared to this STR11 sample. And if you see this DFT pore size distribution, these pores in the STR2/1 get within the complete range from up to 50 nanometers. It means the pores can be retained in the complete mesopore size distribution. So here we can see this the pore volume, which is quite high in case of STR21, and this almost reaches to 1.3 when we obtain the mesopore volume by VGH method. So this is one way approach where we can use higher concentration to induce more pores. The second one, we studied the catalyst concentration and the dilution ratio. So how it can affect the pore structure. So basically, just you decrease the concentration to 0.5, basically it reduces the reaction rate. And with reaction rate, as I mentioned, you decrease the reaction rate, your gelation time will increase, and the network clusters require more time to grow, and you can tune the pores again. So here we can see from almost this is up to 15 nanometer, you can retain more up to 20 nanometers by just simply changing the catalyst concentration. However, your reaction time get increased and you require more curing period. Second, you can also simply change this dilution ratio, like you can have water or ethanol as a solvent, and you just simply, so we just see the results of dilution ratio. With increase in dilution ratio, there is an increase in pore volume. However, that is restricted up to some limit. So there is always a limit in the what we do in the experiments. So another approach, we use the non-polar solvent. So we choose the non-polar solvents using the we have the dipole moment like a benzene, toluene, or cyclohexane. They have zero dipole moment. So we choose benzene, toluene, and cyclohexane. So we see that this is our original sample STR11, and with inducing the non-polar solvent within the precursor, we are getting the improve in the pore sizes and the wider size distribution. So it is from like it is we have 10, so we can get up to almost 18 nanometers with the use of non-polar solvent. Similarly, we also studied different concentrations. So we see that the one stage we are getting some solubility problem. So again, also we see with the cyclohexane, which also has the zero dipole moment, and up to somewhat we can see up to 8 ml of the concentration of cyclohexane in the solution can reach up to higher pore volume, and the retain the pore size is almost in the 15 range. Another approach we see, because what the aim of our study was, is that we generally use the KOH for activation. So we just use some ionic salt that to induce the micropores, but basically we just studied this using the thermoporometry. And here we can see the mesopore size distribution, that there is not much more improve in the mesopores, but there is a steep increase in the mesopore volume. So if you require some specific pore size, then you can use such approach. Then another approach we use, just replacing this our F127 by different block polymers like P123 and 108, just one with the lower molecular weight, one with the higher molecular weight. And we can just simply see that we have the initial represented by the black line, and we can see with this F10 set with higher molecular weight, you get the similar pore structure as with the STR2/1. And here you can see almost it reaches to 0.66 of centimeter cube gram per volume. And even the pore sizes, you can retain up to overall mesopore range in the 2 to 50 nanometer range. However, in the mixed form, there is not much increase in this pore volume, because there is a decrease in molecular weight, and we can relate it with the micelle concentration. So another approach, we use other surfactant like P123 here, and we just see that with P123 there is some phase separation in the solution. Means there is a polymer rich phase and the dense phase in the initial stage. So we use in a combine, and we see that in the combined form it shows the better results for 1:2.57 ratio of F127, and there is a very little change in the pore size distribution. So we can see that F1018 is better when compared with the other template sources. So with this, I just summarize my work that we use different approaches in the carbon monolith tuning the porosity, and we can see with pluronic there is a change in catalyst or dilution ratio and incorporation of non-polar solvents and the use of mixed pluronic form. So you can get the mesopore sizes in the 5 to 50 nanometers, and the mesopore volumes obtained by DFT or BJS in the range of from 0.25 to 75 centimeter cube gram or almost up to 1.3. So basically these value just application of some theories, but you get a better monolith form. And currently we are studying such kind of monoliths for CO2 capture, hydrogen storage, supercapacitor application, as well as heavy metal removal and the organic removals. So with this, I conclude my presentation, and I would like to thank the funding agencies I listed here and my university. So thank you very much. And if you have any question. Yeah, if you have any question, please let me know. Yeah, Abhishek.
Abhishek. Am I audible?
Yes.
Yeah. Good evening, sir. This is Abhishek from CSR NIDI.
Yeah.
Sir, I just want to know, like, you are whatever you are synthesizing monolith material, you are using that material for the environmental application or not?
Yes, currently we are studying adsorption and the electrochemical application. So we are doing some experimental part related to adsorption of phenols, organic dyes, heavy metal removal. So we induce some functionality as well as some heteroatoms. We also use some metal nanoparticles as well as some incorporation other forms of carbon allotropes like graphene or carbon nanotubes.
Okay,
So
okay.
currently we are working on that.
Yeah, okay, sir. Thank you, sir.
I hope there are no more questions. Thank you, Dr. Madhacharan, for the wonderful talk. Okay, moving on. I invite Dr. Shiva Lamichan of Department of Physics and Astrophysics, University of Delhi, to have a short invite lecture on the topic Enhanced Resistive Switching Characteristics in BFO WO3 bilayer thin film structure.
No, no, you are not audible.
Hello.
Yes, yes, yes. Now you are audible.
Okay, sir. Thank you, sir.
Okay.
My screen is visible, sir.
Yes. Put it in full screen mode, please.
Okay, sir. Is it right?
Yes, yes. Perfect.
Okay, sir. Okay. Good evening, all. Myself, Sival Amichane. I am from Department of Physics and Astrophysics, Delhi University. And today, first of all, I am very much happy to participate in a short invited talk in ICN 2022. And thank you all. And today I'm presenting the enhanced resistive switching characteristics in BFO-WO3 bilayer thin film structure. And the other co-authors of this work are Dr. Savita from Kalindi College, Delhi University, Professor Monica Tomar from Miranda House College, Delhi University, and Professor Arjit Chaudhary from ANDC, Delhi University. So, first of all, this is the bismuth ferrite, the material of choice. This is very well-known material, and it has rhombohedrally distorted perovskite ABO3 like structure having lattice parameter ABC equal to 3.96 angstrom and alpha beta gamma all are equal to 89.4 degree in rhombohedral representation. It is the room temperature multiferic material having enhanced polarization value of reported value of 60 microcoulomb per centimeter square. And it has the band gap of the order of 2.7 electron volt, high value of Curie temperature of the order of 1103 Kelvin, and high value of Nil temperature of the order of 643 Kelvin. These are some issues and concerns. Although the bismuth ferrite is the room temperature multiferic material, but due to some issues like appearance of secondary like appearance of secondary phase owing to highly volatile nature, like frequently fluctuation from Fe3 plus to Fe2 plus. So these properties actually hinders its practical application in bismuth ferrite based devices, and also it has weak magnetic characteristics. And these may be the possible solutions. Use of epitaxial matched substrates for single crystalline thin films. And another method is material engineering by doping BFO with rare earth elements or transition metal ions. And the next is making multi-layered structure with BFO and other insulating thin films to achieve the desired functional properties. In our work, so according to literature surveys, there are various materials which were doped and making a bilayer, multi-layer with other materials with BFO by using different techniques to make BFO more applicable. In regarding to this, in our case, we choose tungsten oxide and to make the bilayer. And these are the some prominent features of tungsten oxide. These are the structural parameters. It has the crystal structure of tungsten oxide is temperature dependent. It depends upon temperature. It is tetragonal at temperature above 740 degrees Celsius, orthorhombic in the range of 330 degrees Celsius to 740 degrees Celsius, monoclinic from 17 degrees Celsius to 330 degrees Celsius, and triclinic from minus 50 degrees Celsius to 17 degrees Celsius, and again monoclinic from below minus 50 degrees Celsius. And the most common structure of WO3 is monoclinic with space group P2 1 by N. And it has formula of WO3 and it has molecular mass 331.84 gram per mole, and it has high density, high melting point, high boiling point, and it is the N type of semiconductor due to the oxygen vacancies, because oxygen vacancies are responsible for N type behavior. So we used, basically there are different methods in literature, but we choose RF magneton sputtering for the deposition of WO3 thin film in glancing angle deposition mode. Actually we choose different glancing angle like 65 degree, 70 degree, 75 degree, and 80 degree. And similarly, above the layer of WO3 thin film, bisulfite thin film was deposited by using pulse laser deposition technique. And actually, this work is different from other reported work because two different methods, sputtering and pulse laser deposition, were used to deposit different layers of BFO and WO3 to make BFO more applicable. And for the electrical measurement, 40 nanometer thick circular gold electrodes were grown over BFO WO3 bilayer thin film structure using thermal evaporation technique, and ITU was used as the bottom electrode. Kitle 4200 semiconductor characterization system was used for the electrical measurement. These are the structural, morphological, and other. These are the basically, this is the Xrd diffraction pattern of BFO WO3 over silicon. Actually, we used 3 substrates in a single run, in a single deposition. Silicon, ITO, and Corning for different characterizations. This is the Xrd pattern of all the deposited BFO WO3 thin film by varying the glancing angle from 65 degree to 80 degree, and this is the morphological property by using atomic force microscopy on different samples deposited at 65, 70, 75, and 80. 75 and 80. These are the FSM images of BFO WO3 bilayer thin film structure deposited at different glancing angle 65, 70, 75, and 80. The table shows the different parameters and the different results obtained after the characterization. These are the crystallized size of WO3 and BFO layers. This is the roughness from AFM. This is the leakage current by using Kitle 4200 characterization system, and this is the particle size by using FSM characterization. From this table, we can conclude that at 70 degree glancing angle, the film, both of the layer exhibit the higher crystallinity of the order of 28 nanometer and 37 nanometer of WO3 and BFO thin films, and higher roughness of 30 nanometer, and least leakage current value of 1.5 into 10 to the power minus 8 ampere per centimeter square, and the particle size, enhanced particle size of the order of 25 nanometer. Now I am going to explain about resistive switching. The resistive switching is the refers to the physical phenomena in a dielectric material under the action of strong electric field or current. This type of switching, this type of change in resistance is non-volatile and reversible. And mainly in the present time, this type of properties can be applicable in the random resistive random access memory (RAM) devices, which can be also termed as the MEM registers devices, which is the term found by the combination of two terms, memory and resistance, give the MEM registers. So this type of applications are observed in the dielectric material, and in our case BFO WO3, this is the ferroelectric and the dielectric combination of both materials. And in figure, this is the figure first and second explain about the mechanism of resistive switching. In our case also, the bottom electrode is ITO coated glass, the metal oxide.
Excuse me, Dr. Shiva.
Yes, ma'am.
Your time is about to.
Okay, ma'am. Okay, ma'am. Just. There are two types of resistive switching characteristics on the basis of applied polarity: unipolar resistive switching and bipolar resistive switching. And these are the characteristic curves, resistive switching curves, which were obtained at different glancing angle, 65, 70, 75, and 80 degree. And the different properties are due to the variation in intrinsic defects, oxygen vacancy in the film due to the thermal annealing process. And these are the current conduction mechanism. By the overall explanation, at lower voltage, ohmic characteristics was dominated, and at higher voltage, SCLC and Child's law were dominated. Thank you.
presentation.
Is there any questions? I hope there are no more questions.
Yes, ma'am.
Thank you, Dr. Shiva.
Okay, thank you, ma'am. Thank you so much. Thank you all.
Okay, let's move on to the next session. Let's post the presentation. I invite Dr. Abhishek Sharma of Academy of Scientific and Innovative Research.
Am I audible?
Yes, you are. May I tell few rules? You are only allowed to present 3 slides, and you will have to take only 5 minutes for your presentation.
Yeah. My presentation is visible.
Yes, can you please make it the full screen? Yes.
Yeah.
Yes.
Can I start? Yeah, very good evening to all. I am Abhishek Sharma. I am pursuing my PhD from CSIR Nagpur. My title of the poster is Modulating Morphology of Iron Silver Bimetallic Nanostructure through Photo Oscillation of Ferropheric System and their Environmental Application. As we know, many researchers have synthesized nano-scaled AGFE bimetallic nanomaterial, but the synthesis of oriented and organized bimetallic framework is very tedious process. Traditionally, oriented growth is achieved by using either hard and soft template that dissolve in solution and provide the structural guidance to the nanostructure. Even though synthesis of such architectural diversity with controllable orientation requires stringent conditions such as long reaction time, slow reaction kinetics, sophisticated procedure, and uses of organic solvents. After that, there are no guarantee that procedures provide the desirable products. By intrigued by this idea, we have introduced rapid and one-pot facile synthesis process for the synthesis of hierarchical AGFE bimetallic nanostructure. Now come to my purpose of the study. Herein we have morphologically modulated the AGFE bimetallic nanostructure through photo oscillation process. Furthermore, we have checked the environmental application of such removal of arsenide from aqueous suspension as well as we have elucidated the antibacterial activity of synthesized nanomaterial against both gram-positive and gram-negative bacteria. Now come to synthesis of bimetallic nanostructure. Now these are some of the reaction condition of synthesis process. We have proposed 2 conditions. The first one is the dark condition and second is the light condition. Herein we can see that in condition 1, in aqueous silver ions and the presence of, in condition 3, the presence of iron ions. Herein we can see in the dark condition as well as in light condition, there is no such change in the color observed. While herein we can see the little pale yellow color is observed under the exposure of visible light after the 24 hours. Along with herein we can see under dark condition, the mixture of silver and iron, we didn't get any change in color or precipitation occur throughout the reaction. While under the exposure of visible light, we have observed the change in color, which is bluish gray color, and the precipitation occurs during the within the 5 minutes. This is very rapid reaction to synthesize any bimetallic nanostructure. Let's come to the modulating morphology of bimetallic nanostructure. Herein we have investigated the impact of relative concentration of the reactant on the morphology of synthesized material. Herein we can see different molar concentration or molar ratio of Fe and Ag. In figure 1, the molar ratio is 0.1. Herein the iron is 20 millimolar and silver is 2 millimolar. We can see the initiation of synthesis of nanoparticle. With the molar ratio 0.25 and 1, we have observed, in both conditions, we have observed the spherical and scattered structure of bimetallic nanoparticles. This is because of the presence of higher ample amount of ferrous oxide and hydroxides, which hampered the structural morphology of the bimetallic nanoparticle. While in case of with the molar ratio 1:1 or 5, here in the iron is 5 millimolar and silver is 5 millimolar, and in the molar ratio 5, here is the iron is 1 millimolar and silver is 5 millimolar. We can achieve a distinct coral-like structure of synthesized bimetallic AgFe nanoparticle. Now come to the sorry. Now come to the Xrd. Herein we can see there is no change in Xrd by changing the molar concentration of the. This means the crystal structure is not hampered by the chemical composition. Herein we can see the 0.1 molar ratio, 0.25, 1 and 1. There is no crystal is structure in hampered by the chemical by changing the chemical composition. The sharp peak of sorry, ma'am. Wait a minute. This is the last one.
Okay, continue.
The sharp peak of ferrosulfuric and Ag validated the crystallinity of the AgFe nanoparticle. Now come to the XPS. This is the plot of Ag 3D 3/2 and 3D 5/2. The change in the 6 electron volt means there is a reduction of Ag plus to the Ag naught, and this validated the formation of Ag naught particles. In that XPS, it represented the presence of both Fe3 plus and Fe2 plus of 2p1/2 and 2p3/2 material. That means in the synthesized material, we have both ferrosulfuric material. In the XPS plots, we can see the both iron and silver in the prominent concentration. This is the plot of TEM image. This is the silver embedded ferrosulfuric framework, and the figure B represented the monocrystallinity of the silver iron with 111 lattice plane and with the D spacing 0.236 nanometer. And herein we can see this is the multiple lattice. This occurred due to the Oswald wrapping during the synthesis. This is the elemental mapping of the AgFe bimetallic nanoparticle. The yellow one is the Ag and the pink one is the silver. Herein we can see the silver is homogeneously distributed throughout the ferrosulfuric framework. Now come to the mechanism, which is the main part of my reaction. We have introduced synthesis process into 6 stages. The first is the autocatalytic photooxidation under the exposure of visible light. The Fe.
It's
Yeah, please.
your time is exceeded.
Okay.
This conclude.
Okay. I'm going to finish very soon. This is the autocatalytic photooxidation. Here in the Fe2 converted to Fe3, and further in the exposure of under the exposure of photoactive, the Fe3 is converted to FeO and FeOH. This is the most dominant species during the reaction because it formed the oxide and hydroxide of iron. And in the same time, the photo dissociation and photo oscillation occurred. It is a chain-like structure, a chain-like reaction. It is a Fe2, Fe3, and Fe2 reaction occurred simultaneously. In the same time, the formation of Fe oxide occurred, and due to the presence of electron pool in the reaction system, the Ag plus also reduced to converted to Ag naught. And finally, with the reaction between the Ag naught and Fe2 and Fe3, it formed a distinct coral-like AgFe bimetallic nanostructure. Now come to the environmental application. As we know, the arsenite are the most common problem throughout the globe with high affinity to thiol group. Under the several reaction conditions, the synthesized nanomaterial have promptly removed the arsenite from 1000 ppb to 10 ppb, which is safeguard under standard limit of arsenite, US EPA and WHO. Along with, we have checked the antibacterial activity against the gram-positive and gram-negative bacteria. Here in the E. coli is the gram-negative bacteria. We can see the zeta potential of the synthesized material at the several pH. My material is showing the positive zeta, and here in the E. coli is the negative one. That's when due to the electrostatic interaction between the material and the bacteria, the MBC achieved at 32 mg per liter of the Ag concentration and in the material. And for the gram-positive bacteria, which is Macrobacterium, Due to the van der Waals interaction and the high surface to volume ratio, with the optimum dose 64 mg per liter of silver ion in the presence of nanoparticle, MBC attained in the MBC attained. Now I am concluding my research. We have introduced the rapid and one-pot synthesis of coral-like structure, employing the photo-oscillating behavior of ferrocerific system in the aqueous medium. We have eliminated the extramural surfactant or template for the synthesis of stabilizing the bimetallic nanostructure. We have promptly tailored the morphology.
Hello, Mr. Abhishek. It's already time over.
Okay, thank you. We have published my paper in ACS Chemistry of Material in 2021. Thank you so much.
Okay, Abhishek. So, what's exactly what is the novelty of this work?
The novelties of this work is generally the bimetallic material is formed by using the reducing or capping agent, but herein we have synthesized the hierarchical structure without using any reducing or capping agent. This is the novelty of the work. And this is very rapid reaction. Generally, the bimetallic structure are formed with it's a tedious and time-consuming reaction system. But herein, we have synthesized within 5 minutes the bimetallic structure, like a coral-like.
Is it a review? Is it the work from the review paper, or is it an original work done by you?
Sorry, I'm not getting you. Your voice is breaking.
My question is this work done by you, or is it a review work?
It's my lab work. My colleague, my senior, I work with him, and we have published the papers together.
Okay, okay.
Is there any other questions? No more, then we can go for the next participant.
Thank you so much.
Thank you, Abhishek. Kindly, every participant, kindly note that you will be having only 5 minutes for the presentation. Kindly mind the time.
Kindly note that 3 minutes presentation and 2-minute discussion.
Moving on to the next person, I invite Ms. Ardra Vijay PV of Shankar Memorial SNDP Yogam Arts and Science College, Koilandi, India.
Madam, I am Babina. May I present Ardra's slides because I think due to some technical reasons she couldn't attend. That's why I am the corresponding author of that paper. May I present slides?
Yes, you can.
Yeah, okay. Is it visible?
Yes.
Okay. It's actually an MSc project work, and Ardra Vijay is an MSc student at R. Shankar Memorial SNDP Arts and Science College, Koilandi. And I'm the Babina Ninoramittal, and for this work, zinc selenide nanomaterial was synthesized by one-pot method, that is by solvent thermal method, and the highlights of this study is a minimum precursors used and just investigate its activity, its photocatalytic activity. also, and through characterizations, the Xrd DRS and STEM FDR and elemental mapping in SEM, we have confirmed the formation of zinc selenide ZnSeO4, and the application, photocatalytic application, was analyzed, investigated. Further studies related to this properties and applications of this materials are going on, but actually in this work we have just checked this whether it is photocatalytic active or not, and it is almost 65% photocatalytic degradation of methylene blue was happened by using this material, and compared to pure methylene blue degradation, it takes 60 minutes for the this much degradation. So other further applications of this by using this material is going on, and okay, thank you. Hello. Main highlights of this study is this material is very novel material, not yet reported, and minimum precursors were used for this synthesis, and solvothermal method is used for this, and ethylene diamine is a solvent used for this preparation. Okay, thank you.
Okay, the session is open for questions. Okay, if there is no question, thank you, Babina.
Oh, thank you.
So we can move on to the next participant, Deepti Ranjan Paital, Indian Institute of Technology, Gandhinagar, Gujarat, for presenting designing plasmonic goal TNP at MNOX partial nanostruct towards efficient photoelectrochemical
water oxidation. Am I audible?
Yes, you are audible.
Thank you, sir, for the introduction. So, good evening, everyone. So, I'm a PhD student working at IIT Gandhinagar. So, my topic is designing a plasmonic AUTNP manganese oxide-based core cell nanoconstruct towards the photoelectrochemical water oxidation reaction. Especially, solar light-driven hydrogen production from water is a viable route for our renewable energy infrastructure. But for this, we need a photocatalyst. But the available photocatalysts have their limited due to their low photostability and their narrow band gap, mainly in the UV range. But we know from the science that the only 1% of the solar rays is in the UV range, which is falling on the Earth's surface. And in order to utilize the visible and the NIR range, we need a suitable photocatalyst. In this regard, gold plasmonic nanoparticle has been in intense interest due to its tunable optical properties. This is the surface plasmonic resonance. As you can see from the figure, tuning the shape of the nanoparticle, we can tune the absorbance window. Therefore, we can tune the light harvesting to produce hydrogen. Mainly, plasmonic nanoparticles, both photothermal, hot electrons, both are participate to enhance the catalytic activity. But to separate them confidently is a very difficult task. Here, first we prepared a triangular prism of gold nanoparticle, as you can see from the TM images in the figure B. A triangular gold nanoparticle prepared, then we deposit a manganese oxide on top of this nanoparticle weight chemically and done their characterization from the UV absorption spectroscopy. You can see 32 nanometer of the redshift is observed from the UV split, and from the stem elemental mapping, you can see a clear contrast of the cell of manganese oxide on top of this gold nanoparticle. Furthermore, to study the water oxidation activity, we perform the electrochemical study. Then here as from the figure A, as you can see here, a clear synergistic effect of the gold nanoparticle and the manganese oxide has been observed, as the onset potential for this is very minimum and the catalytic current is very high compared to gold TNP and the blank ITU. And we check this photocatalytic activity by shining light on these nanostructures, and as you can see, the catalytic current as well as the decrease in onset overpotential is also observed. To verify this effect is due to the plasmonic effect, which is if this is due to plasmonic, we perform the LSP measurement at different wavelengths, varying their power. As you can see from the figure, this figure, the onset change in the onset of potential relatively matches with the extinction spectra of this nanostructure, which clearly tells that this is due to the plasmonic effect. Furthermore, we check the onset of potential by varying their power. As you can see here, the onset of potential decreases almost linearly with the intensity of the laser. Furthermore, to study the whether this is the photothermal effect or the photocatalytic effect, we studied the chronoamperimetry and check the overall photocurrent time trace shape during this process. As you can see, in 532 nanometer laser, there is a fast component as you can see here, and in the inside of this, followed by a slow component. However, in case of 635, the fast magnitude of fast component is very less, and the slow component is magnitude of slow component is higher. So we assign this fast component as the photocatalytic effect and the slow component as the photothermal effect. Based on this calculation, the magnitude of photocurrent, we calculate the contribution of photothermal, that is I slow, and the photocatalytic effect as the phi fast. So as you can see, the in 532 laser, the photothermal effect in all the laser is higher, but in case of 532, only the photocatalytic part is higher. To verify this mechanism, we done the power dependent study. As you can see here, by tuning the laser power, we can see the change in increase in the magnitude of the photocurrent. To understand this mechanism behind it, you have to consider the two processes, like the hot carrier generation and the relative position near to the Fermi level. In case of 532 nanometer laser, as you can see here, the intense D band holes are created, which are easily abstracted by this manganese oxide layer, as you can see here, and these holes can be these holes can contribute to the fast component. On the other hand, at the 808, the holes are created much above near to the manganese oxide layer, so that these holes are not extracted. Therefore, they are getting they are thermalizing more. Therefore, we are getting more thermal effect. So, in summary, we have designed this core cell nanoconstruct of gold, prism, and manganese oxide, and check their excellent water oxidation activity, so that we can get a hydrogen from this process. And the major finding is that we are getting photothermal effect is a major factor which is playing a important role. Instead of the previous report, mostly photocatalytic part is plays a important role, but here we conclude that this
Hello,
photothermal effect playing the role.
Dipiranjan.
Thank
Please
you.
conclude.
Yeah, it's done. Thank you, ma'am, and you can ask any question. Any question? Hmm.
The session is open for questions. Anyone? Deepranjan, can you comment on the novelty?
Yeah, because as in the last slide, as I mentioned, most of the photocatalytic process you mentioned, like the photocatalytic, the hot electron transfer plays a key role, right? But here we are getting the thermal effect, which is like when these electron and hole pairs are not extracted, they are thermalizes, and this thermal, the increase in the solution temperature, plays a key role in enhancing the catalytic activity. So am I clear?
Yes, it is fine. So thank you, Deepranjan. We can move on to the next
Thank you,
presenter.
sir.
So I invite Mansoor Binate, Basic of Science, Chemistry Department, University of Virjat, Iraq, on the topic basic applications of magnetic nano catalyst doped with copper metal in the oxidation of benzyl alcohol under aerobic conditions. Manso? Okay, if he's absent, we can move on to the next presenter. N. Madhu, Department of Physics, Government Arts and Science College, Kozhikode, Kerala, India, on the topic of synthesis and characterization of tin oxide nanoparticles for the gas sensor applications.
Okay, sir. Is it visible my slide?
You're audible, but no slides are not visible.
Okay. Wait 1 minute. But it is not sharing.
Can you share the entire screen option?
Yeah. That's but there is no share option. Only cancel option is there.
Excuse me, what happened?
The share button is not working. It is not. 1 minute.
Can you re-log in?
Okay. So no. It's not working. The share button.
Okay, can you leave the meeting and join once again? By that time, we'll call the next person. You can present.
Okay. Thank you.
Next, I invite Purbajyoti of Institute of Advanced Study in Science and Technology, Guwahati, Assam, to present on the topic optical properties of small titanium nitride nanoclusters.
Hello, ma'am. Am I audible?
Yes, you are.
Is my screen visible?
Yes.
Good evening, everyone. I am Purbajyoti Bhagawati, currently working as a PhD scholar in the Computational Material Science Group of Institute of Advanced Study in Science and Technology, Assam. Today, I am going to present a poster on the title Optical Properties of Small Titanium Nitride Nanoclusters from First Principles Calculation. So it is well known that titanium nitride is a refractory material having very high melting point and chemical stability. They show optical properties which are suitable for the application in the field of plasmonics. Due to their superiority over the conventional plasmonic materials like gold and silver, titanium nitride is nowadays used as alternatives in many hostile environments. The bulk titanium nitride has been studied very rigorously, but the nanocluster system was remain untouched to the best of our knowledge. So for the first time, we have generated some small nanocluster systems of titanium nitride and reported recently. So we have used these computational parameters and these software packages for the generation of these nanocluster systems. So these are very small nanocluster systems of titanium nitride. So based on these structures, we have calculated the optical behavior of these nanocluster systems on the basis of the complex dielectric function and absorption spectra. So in this figure, we can observe that in all the plots, the real part of the complex dielectric function, that is epsilon1, is positive. So this is due to the fact that the external electric field we are applying to part of the system induces an excitation among the free electrons of the system. The free electrons then experiences an induced field among them, and when the external field oscillates too fast, then the induced field cannot keep pace with it and gives rise to some positive values of epsilon1. And we can see from these plots that in high energetic region, epsilon2 is tending towards 0. So this indicates the metallic behavior of the nanoclusters. And also epsilon 1, it tends towards unity. So these properties make the systems transparent in the high energetic UV region with low amount of absorption. So these are the plots for density of states and band structure. So from this, we can see that there is a direct transition, direct interband transition. So this is due to the transition between the NP and TID electrons. So here we are observing a sharp peak. So this is due to the direct transition between the NP and TID electrons. So again, we have plot the absorption spectra for the nanocluster systems. So here we are observing some small peaks throughout the whole energy range. So these spectra are very sensitive to the geometry of the cluster. The small peaks in all the clusters is due to the fact that our nanocluster systems are non-symmetric in nature. And the starting of the spectra from zero photon energy indicates that the structures are metallic. So in nanocluster systems, the blue shift of the absorption peaks. So it is very common, that is the shifting of the peaks towards the low energy region with increasing size. So in our case also, we have compared the absorption peaks of Ti4N4 and Ti10N10. So we are observing here also the shifting of the absorption peaks towards the low energy region. So in conclusion, we have found that the plasmonic behavior of the titanium nitride system, like in case of bulk system, so it is missing in the case of these nanoclusters. So this is due to the fact that these nanocluster systems are very small, and also the UV transparency so makes the nanocluster systems to be used as a protecting layer in solar cells. So with this, I conclude my poster. So these are some of the selected references I have used in making this poster. So I want to acknowledge my institute, ISST, DST Inspire for the Fellowship, Permission Supercomputing Facility of IIT Guwahati, and especially the organizers of ICN 2022. Thank you.
The session is open for questions.
Okay, let me ask you a question. Why did you opt for titanium nitride?
Okay, so as I have mentioned, some plasmonic materials are conventional plasmonic materials are gold and silver, so they are being used and means huge amount they are being used, but the melting point of gold and silver is very low. So in some harsh environments like high pressure region and high temperature region, so gold and silver cannot be used. So but the melting point of titanium nitride is very high, around 2900 degrees centigrade. So this is the main reason for choosing titanium nitride. So it can be used as alternative plasmonic materials in some harsh environments. And also their optical properties are similar to gold and silver, but with an advantage of high melting point.
Okay, is there any other questions? If there are no more questions, thank you, Pubajodi, for the talk.
Thank you, ma'am.
Next, I invite N. Madhu, Department of Physics.
Okay, I'm presenting.
Okay.
So now also there is a problem. I can't share the content, share the PPT.
Okay, you can mail your PPT.
I have already mailed. I have already.
Okay. Okay, by the time we'll call the next one, I invite Binila K. Kora, School of Chemical Sciences, Mahatma Gandhi University, to have the talk on bio-inspired nitrogen-doped carbon dots as a dual-mode probe for tetracycline and mercury ions.
Okay, thank you. Is my slide visible? Hello?
Yes, yes.
Good evening, all. Myself, Bindlake Kora. I'm a research scholar at School of Chemical Sciences, Mahatma Gandhi University, Kottayam. My topic of presentation is bio-inspired nitrogen-doped carbon dots as a dual-mode probe for tetracycline and mercury ions. Carbon dots are carbon nanoparticles with a size less than 10 nanometer. It can be synthesized from green and chemical precursors. It has several properties such as aqueous dispersion, non-toxicity, stability, and high fluorescence. So the major objectives of the work are to synthesize NCDs from curcuma amida and triethylene tetraamine using hydrothermal method, and characterize using different techniques for identifying the morphological and optical features of the NCDs. Fluorescence detection of tetracycline using inner filter effect based fluorescence quenching process, and electrochemical detection of mercuric ion using electron transfer mechanism. The synthesis procedure is described here. First of all, the curcuma amida extract was taken. It was mixed with the triethylene tetraamine and it was treated hydrothermally at 200 degrees Celsius for 7 hours. Brown colored solution was obtained. It was filtered and centrifuged and stored at low temperature. Some of the major characterizations for NCDs is shown here. This is the XPS analysis data. XPS analysis was done to confirm the elemental composition, and it was found that 3 major peaks were observed at the XPS spectrum corresponding to carbon, nitrogen, and oxygen. These are the high resolution spectra of C1s, N1s, and O1s. The absorption spectrum of NCD is shown here. 2 peaks were obtained. One peak at around 350 nanometer and other at 270 nanometer. This corresponds to the N to pi star and pi to pi star transition, corresponding to C double bond O, C double bond C, etc. And FDR spectrum was also recorded to find the different types of functional groups, and it was found that several functional groups such as hydroxyl, CH, CN, C double bond C, CO, etc. are present. These are the 10 images of the carbon dots. Well dispersed and spherical carbon dots were obtained, and its diameter was found to be 7 nanometer. Its fringe width was found to be 0.22 nanometer. This corresponds to the 002 plane of graphitic carbon. SID pattern was observed, and this confirms the amorphous nature of carbon dots. Coming to the application part, it was mainly applied for 2 applications. First one is fluorescence sensing of tetracycline, and second one is electrochemical sensing of mercuric ions. With the increase in concentration of tetracycline, the fluorescence intensity of the carbon dots synthesized decreased. That means with the addition of tetracycline, a fluorescence quenching was observed. A linear plot was obtained when F0 by F was plotted against the concentration, and the limit of detection was found to be 32 nanomolar. In order to find the mechanism behind this fluorescence quenching process, the absorption spectrum of tetracycline and excitation spectrum of NCD was recorded. A complete overlap confirmed that the mechanism can be an inner filter effect or Foster resonance energy transfer. Lifetime analysis of both the systems, that is NCD and NCD plus tetracycline, confirmed that the mechanism is an inner filter effect process. Inner filter effect means the second absorber. That means that here the quencher absorbs the frequency, absorbs the emission of carbon dots. And coming to the second application, that is electrochemical sensing of mercuric ions. Here we can see the cyclic voltograms of bare glassy carbon electrode, NCD coated glassy carbon electrode, and NCD coated glassy carbon electrode in the presence of mercuric ions. As it is clear from the graph, in the presence of mercuric ions, an oxidation and a reduction peak is appeared. But in the presence of other metal ions, no such peaks were observed. This shows that the developed sensor, that is NCD by GCE, has the potential for sensing mercuric ions among other ions. This is the electrochemical impedance spectra of bare glassy carbon electrode and NCD coated glassy carbon electrode. And it is clear that NCD coated glassy carbon electrode has a smaller semicircle. This confirms that it has more conductance than bare glassy carbon electrode. With the increase in concentration of mercuric ions, the current also increases. A linear plot was obtained when the current was plotted against the concentration. The limit of detection was found to be 0.2 nanomolar. Coming to the conclusions, highly photoluminescent carbon contradots were prepared through hydrothermal method from the root of curcuma amida and triethylene tetraamine as the precursors. It is applied for two major applications, for the fluorescent sensing of tetracycline and for the electrochemical sensing of mercuric ions. So this is all my presentation. Thank you.
Hello, Harsha Haridas. You can ask.
Hello. Yes. I have a query about why you have chosen TTA as your precursor.
Because there are several precursors like ethylene diamine, triethylene tetraamine, etc. I choose triethylene tetraamine because there are four amino groups present here in triethylene tetraamine. That's why I chose triethylene tetraamine as the nitrogen precursor.
Okay. Thank you.
Is there any other questions? Okay, if there are no more questions, we'll move on to the next one. Okay, and Madhu, now you can present. And now you can proceed with PowerPoint.
We will share the PowerPoint.
Okay. Hello. Hello.
Yes, you are audible.
Okay. First of all, I'm thankful to the organizer of this conference for giving me such an opportunity to participate in this conference. And my presentation is just about the synthesis and characterization of tin oxide nanoparticles. So the importance of this synthesis process is it is very easy and very cheap, and we can use the tin chloride as precursor, and then some NaOH and some surfactants, sodium dioxide, and here I synthesize the tin oxide nanoparticles using this technique. And the most important of this work is that we know that the tin oxide has large variety of applications in gas sensors, and we can extend this application to the pressure sensing also. So first of all, we have to construct the tin oxide nanoparticles by using this precipitation method. And here in this work, the characterization techniques we used. First, we studied this morphological and structural studies using SEM and Xrd. And then the vibrational modes and the possible vibrations are studied using FTIR spectra. And the semi-images gives the size and the morphology. And finally, the UV visible spectra for getting the band gap. The Xrd data confirms the JCVDS data confirms the formation of the tin oxide nanoparticles and its tetragonal structure. So the crystallinity can be shown using Xrd pattern. Then the FTIR spectra, the peaks confirms the formation of SN or SN bending modes and other OH vibrational modes. And some water molecules are also there, which is trapped in the crystal structure. And the semi-image, we can get the average particle size is also present here. So then finally the UV visible spectra, we can show the peaks in a range, and the energy gap is found in almost 3.75, sorry, 3.45. So the application of this work is we can apply the zinc oxide nanoparticles formed in different gas sensing applications as well as pressure sensing applications. So we can control the particle size, different pH. By controlling the pH, we can so the application lies in the gas sensors and pressure sensing applications. So this is the conclusion. Okay, thank you.
So the session is open for questions. Anyone? So if there is no further questions, we'll move on to the next contestant. Thank you, Madhu.
Okay, thank you.
So I will invite the next participant, Bonnie K. John, School of Chemical Sciences, Mahatma Gandhi University, Kottayam, Kerala, on the topic of microwave-assisted synthesis of nitrogen-doped carbon quantum dots as a fluorescent sensor for amoxicillin.
Okay. Is my screen visible?
Yes, it is visible.
Okay. Good evening to all. Welcome to my poster presentation entitled Microwave-Assisted Synthesis of Nitrogen-Doped Carbon Condots as a Fluorescent Sensor for Amoxicillin. C2Ds are zero-dimensional semiconductor nanomaterials composed of sp2 hybridized graphite carbon atoms. During the doping the C2Ds with the heteroatoms is an interesting and efficient technique to enhance the quantum yield of C2Ds. Among various elements, the size similarity between nitrogen and carbon atoms allows effective doping. In this work, I have synthesized nitrogen-doped carbon quantum dots from the precursors beta-cyclodextrin and EDTA by mixing it with 2 molar sulfuric acid and water, followed by an micro-irradiation for 12 minutes at 450 volt. After micro-irradiation, we get a brown-colored solution which were filtered through an nylon 6 membrane. We get pure brownish yellow C2D solution, which is visible in which is brown under visible light and exhibit a blue fluorescence under UV light radiation. Moving to optical properties, the UV spectral analysis exhibited two characteristic peaks at 213 nanometer and 283 nanometer, corresponding to N2 pi star and pi 2 pi star transition. The PL emission spectra exhibited maximum excitation at 360 nanometer and the emission at 445 nanometer. In order to find out the wavelength at which the fabricated NCQDs exhibit maximum fluorescence, we have recorded PL emission spectra on exciting the sample from 300 to 400 nanometer. From the graph, it is clear that on exciting the sample at 360 nanometer, we get a maximum fluorescence emission. Structural properties. MEDS analysis shows that the fabricated NCQDs contains the elements nitrogen, oxygen, and carbon. Raman analysis exhibited two characteristic peaks, D band and G band at 1356 and 1591 centimeter in base. The SQR analysis shows several peaks corresponding to the functional group OH, NH2, CH3, C double bond O, C single bond O, etc. The Xrd analysis confirmed that the fabricated NCQDs are amorphous in nature with a 2 theta value of 26.04 corresponding to the 002 graphite plane. The TEM images shows that the synthesized NCQDs have a particle size of less than 10 nanometer. The particle size distribution further confirms that the average particle size of the fabricated systems are around 6 nanometer. Further, we have developed the fabricated NCQDs as a fluorescence sensor for amoxicillin. Initially, we have optimized the sensing conditions such as pH and interaction type by mixing NCQDs with amoxicillin at different concentrations, at different pH. From the graph, we can see that at a pH of 4, the maximum fluorescence intensity was observed within an interaction time of 2 minutes. On further studying the interaction of NCQDs with the different drug molecules shows that only in the presence of amoxicillin molecule, a characteristic fluorescence quenching was observed. Further, concentration studies shows that on increasing the concentration of amoxicillin from 0 to 100 micromolar, there is a gradual decrease in the fluorescence intensity. From the concentration study, we can calculate the LOD and the linear range. From the graph, it is clear that the linear range lies between 0 to 25 micromolar with an LOD of 80 nanomolar. And from the indifference study analysis, we can see that even in the presence of other drug molecule, the developed NCQD fluorescent probe can detect amoxicillin molecule selectively and selectively without any interference. The mechanism of PL emission includes can be explored by using PL decay curves and comparison of UV and PA analysis. From the fluorescence lifetime analysis, we can see that there is no appreciable difference in the fluorescence lifetime of NCQDs before and after addition of amoxicillin. And also, when comparing the UV visible spectra of NCQDs, amoxicillin, NCQD plus amoxicillin mixture, and the PL emission excitation spectra of NCQD shows that there is a considerable overlap between the absorption band of the amoxicillin and the fluorescence excitation band of the NCQDs. From these two observations, we can conclude that a combination of static quenching and inner filter effects operate between the amoxicillin molecule and NCQDs. Conclusion. We have successfully synthesized NCQDs with a quantum yield of 15% from a mixture of beta cycloreduction and EDTA. They exhibit a spherical shape and an average particle size of about 6 nanometer. As a PL sensor, they are very selective towards the amoxicillin molecule. The sensing process involves a combination of static quenching and the IFE mechanism. This method exhibits an excellent linear range from 0 to 20 micromolar with an LOD of 18 nanomolar. Thank you.
Okay, the session is open for questions. Bonnie, can you comment on the novelty?
It's novel because actually we use the microwave method for synthesis. It is very, and also very the carbon dot can be synthesized within 12 minutes. And also not much work has been reported for synthesis of NCQDs from beta cycloreduction also.
Okay, any more questions? So if nothing, thank you, Bonnie. We will move on to the next participant. So I will invite Pratik Mohanty, Center for Nanoscience and Nanotechnology, Shiksha Anusantan, Bhubaneswar. for the topic of activated fullerene as efficient electrode material for flexible supercapacitor application.
Hello everyone. Is my slide is visible and am I audible?
Yes. Perfect.
Okay. So good evening everyone. I am Ritik Mohanty from Center for Nanoscience and Nanotechnology, Soha University, going to present my poster on activated fullerene anchored on zinc cobaltate as efficient electrode material for flexible supercapacitor application. As we know, from powering a remote to and powering an electric vehicle, supercapacitor has become a vital electric component in this arena. So the research on supercapacitor has been boomed in the recent current years due to the emergent energy needs. So as we know, electrode materials plays a vital role in the supercapacitor. And coming to my work, here I have done a by combine. As we know, the pseudocapacity material and ideal state material are individual by their mechanism. But here what I have done, by combining one pseudocapacity material with another EDLC type material to prepare a nanohybrid and evaluated their supercapacitor performance, which not only show the enhanced supercapacitor activity but also showed the long-term stability. Coming to my experimental details, I have used the fullerene and then activated it and put it into the hydrothermal reactor with the zinc cobalt acetate source and by taking urea and ethylene glycol, where the hydrothermal reaction was taken place, and then after washing and drying it was subjected to calcination. Thereafter we got the nanohybrid. So to evaluate its structural and morphological characteristics, Xrd and FSM and TEM has been performed, where in Xrd we can see the proper page formation of both the neat and the composite, and in the morphological analysis we can see the non-uniform anchorment of the activated fullerene over the zinc cobaltate nanosphere. And for the elemental distribution, EDX analysis has been taken into consideration, where the carbon was visible from the EDX analysis. And after that, as we know, the more the surface area and more the activity of the material. So the BT surface area currently evidence about our work that the composite has the more surface area than its needed counterparts. To access the electrochemical evaluation, both the 3 electrode and 2 electrode test has been repeated. And from the CV curve, so we can notice that the activated fullerene anchored zinc cobaltate has shown the more the CV area rather than to its the neat ones. We show the enhanced activity, and the redox curves was attributed to the strong pseudocapacitive nature of the material, and the GCD curves were also associated with the CV curves by showing the distinct plateau-type nature. And the electrochemical impedance spectroscopy also evidence about the less conductivity of the prepared composite rather than the neat material. And the RS plot also evidence about the chemically reversible Faradic reaction that has been occurring on the surface of the electrode. And to know its efficiency for long-term cycle, 5000 cycles were repeated at a current density of 8 ampere per gram. We showed the almost 83% specific capacitance retention after the 5000 continuous 5000 cycle. And the picture G2 is show about the 2 electrode setup, which were currently as similar with the 3 electrode setup results. And coming to the Ragon plot, which also evidence about the enhanced energy density, power density of 36 watt-hour per kg of energy density, and 1681 watt per kg of the power density, which was currently the highest reported state of art material related to these systems. To further know about its flexibility application in the supercapacitor arena, we have done a analysis by taking a CV curves of a unbended device, and after the various rigorous bending cycle, we have then again conducted the CV curves, and both the nature of the CV curves were nearly equal. So we can say its application in the flexible energy storage device. So coming to my conclusion, the solvers normally synthesized sample has gone through the analysis of the Xrd and its morphological and elemental distribution analysis, and it shows the enhanced porosity, conductivity, and along with short diffusion path, which will be able to deliver the super electrochemical property. So this proposed hybrid material can give a pathway to design high performance flexible energy storage devices. So these are my references, and now I am open for questions. Any questions?
Okay, session is open for questions. Okay, if there is no other questions, we can move on to the next participant. So thank you, Ritik Mohanty.
Okay. Thank you.
So the next participants, Neha Matthew, School of Chemical Science, Mahatma Gandhi University, for the topic carbon dot based fluorescent probe for selective and sensitive detection of antibiotics. Neha Matthew. Sneha, you are not audible. Hello, Sneha.
Hello, sir.
Yes. Now it's fine.
Okay, sir.
Please put it in slideshow mode.
Okay, sir.
Yes,
visible. Okay. Good evening, everyone. I am Sneha Matthew, presenting my work entitled as carbon dot based fluorescent probe for selective and sensitive detection of antibiotics. Introduction. Carbon dots are particles with size less than 10 nanometers, and they have exceptional properties like ease of preparation, low toxicity, photostability, and biocompatibility. They are prospective replacement for standard fluorescent semiconductor quantum dots, which have several drawbacks, including heavy metal toxicity, high cost, and potential health hazards. And they find extensive application in fields of sensing, bioimaging, photocatalysis, etc. And I have adopted hydrothermal method for the synthesis of this carbon dot. This hydrothermal method finds simplicity, rapidity, and low pollutant emissions, so is regarded as one of the most used CD synthesis process. And this carbon dot was used for selective sensing of doxycycline. And doxycycline is a tetracycline class antibiotic with beta diketonoid structure, and it's used for treatment of several diseases. But this misuse of this doxycycline would result in major health risks to humans. And the fluorescence and electrochemical based sensing have received a lot of interest in recent years because of their advantages such as high sensitivity, quick response time, and low cost. This is the scheme for the synthesis and application of this carbon dot. This carbon dot was synthesized from a green leaf via hydrothermal method, and this carbon dot exhibit blue fluorescence under UV illumination. Results and discussions. The optical properties of the carbon dot were analyzed using UV visible spectroscopy and fluorescence spectroscopy. The UV visible absorption spectrum shows an absorption maximum at 278 nanometers, which correspond to the pi to pi star transition of CO bonds. And on exciting the carbon dot at 380 nanometers, it shows an emission spectrum at 465 nanometers. And the FTIR spectrum shows the presence of hydroxyl and amino groups in the carbon dot. Then the Xrd spectrum shows angle at 24 degree, which correspond to the 002 Bragg's diffraction plane, and the HRTM image shows that the carbon dot have a apparent lattice spacing of 0.295 nanometers. Then the elemental analysis were done using X-ray photoelectron spectroscopy. XP spectrum shows the presence of nitrogen and carbon in addition to nitrogen and oxygen in addition to carbon in the carbon dot. Then applications, fluorescent sensing of doxycycline. We have used this carbon dot for selective sensing of the antibiotic doxycycline. Among the different analytes we have tested, only doxycycline was selectively sensed by the carbon dot, as seen the sharp decline in the fluorescent intensity. The effect of interfering species were also analyzed. Even in the presence of different interfering species, the carbon dot selectively sensed doxycycline. And on increasing the concentration of doxycycline, there was a steady decrease in the fluorescence intensity. And on plotting the concentration of doxycycline against the fluorescent intensity, a linear plot was obtained with a limit of detection as 0.78 micromolars. And the mechanism was explored using UV visible PL spectroscopy and lifetime measurements, and it was IFE based mechanism. Then we have also used this carbon dot for the electrochemical sensing of doxycycline. The cyclophotometric analysis was shown in this figure A. On comparing to the bare GC, the CD coated GC shows enhanced current response, but on adding doxycycline, there was a sharp increase in the current response was observed. And on testing the selectivities of the carbon dot towards different analytes, we can see that the carbon dot selectively sensed doxycycline among the different analytes. This is the electrochemical impedance spectrum of the carbon dot modified GC and the bare GC. And we can see that the carbon dot modified GC shows lowest resistance and higher conductivity. And this is the stability study of the carbon dot. And the stability study was conducted using a fresh sensor and the one sensor that kept at desiccated 1 month. You can see that there is no much difference in the current responses. Thus, the synthesized carbon dot is highly stable. Thus, we can conclude that we have synthesized a blue fluorescent carbon dot from green sources via the hydrothermal method for the fluorescent and electrochemical sensing of doxycycline with excellent detection limits. Thank you.
Is there any questions?
Thank you.
If there are no questions, let's move on to the next one. I invite Anu Rostako of School of Chemical Science, Mahatma Gandhi University, to present on the topic selective detection of mercury and amoxicillin through electrochemical switch on-off response of carbon quantum dots.
Hello? Hello?
Yes.
Hello? Is my screen visible? Hello? Okay. Okay. Good evening, all. Welcome to my presentation. I am Anaros Chako. The topic of my poster is selective detection of mercury and amoxicillin through electrochemical switch on-off response of carbon quantum dot. Carbon quantum dots are zero-dimensional carbon nanomaterials. They shows unique electronic properties and potential. Hello?
Anu, you can unmute your mic and continue. Anu Rosjanko, you are not audible. Kindly unmute and continue.
Hello?
Yes, you are audible. You can continue.
Okay, thank you. Carbon dots are zero-dimensional carbon nanomaterials. They show unique electronic properties and potential applications. They possess attractive properties like high stability, good conductivity, low toxicity, environmental friendliness. In this work, we synthesized carbon dot from waste paper through electrochemical hydrothermal synthesis method. The synthesis was several advantages. One-step synthetic procedure, cost-effective, eco-friendly, good dissipation in solution. Preparation of CDs. 3 gram of waste paper weighed in a beaker, around 100 ml deionized water added it into and sonicated for 30 minutes. After sonication, transferred it into stainless steel autoclave. After under a high pressure and temperature, the solution turned into carbon quantum dots. The synthesized CD were characterized by various techniques. First, the size and morphology of synthesized CD were analyzed using Xrd. The average size was obtained 4.887 nanometer. Optical properties of CD were measured using UV visible spectroscopy. Two peaks are observed at 205 nanometer and 275 nanometer. The functional group of CD identified using FTIR. The presence of different oxygen functionalities was confirmed. Next is Xrd. The amorphous character of carbon reflected in Xrd pattern. Finally, XPS. Measurement were carried out to know the chemical state of carbon and oxygen. So next we move on to the electrochemical metal drug study. This was explained through switch on off platform. After the practical optimization, we carried out electrochemical sensing in 0.1 molar PBA solution. First, we screened CD carbon quantum dot affinities towards different metal ions. Only Hg ion shows significant redox peak among the other metal ions. Hence, it was explained as switch-on state. The DPV and CV were used to check the effect of concentration of mercuric ion. Based on calibration plot, we get 5.5 nanomolar as limit of detection. The stability of CD was monitored daily. After 25 days, there was a small decrease in current response compared to initial response. Next is in anti-interference study. Anti-interference study of carbon quantum dots revealed that redox signal of mercury CD was unchanged with other metal ions. Next, we examined the different affinity of CDs towards different drugs. Then we found that peak current of HGCD decreases in the presence of amoxicillin out of other drugs. This detection was termed as switch-off state. Again, DPV and CV were used to check the effect of concentration of amoxicillin. We get 16.3 nanomolar as limit of detection. To know the electron transfer resistance of CD and its analyte complexes, by electrochemical impedance spectroscopy. When the peak current is increased, resistance is decreased, then the surface of semicircle is also decreased. Comparing all the characterization and electrochemical result, the developed CD as a successful electrochemical switch on, electrochemical on-off switch. Okay, this is all about my presentation. Thank you.
Okay, yes. The session is open for question. Okay, Anurus Chako. Hello.
Hello.
Yes. How about the cost effectiveness?
Hello. Hydrothermal method is only needed autoclave, stainless steel autoclave. The initial payment is only hello.
Anurus Chako, we can't hear you.
Hello.
Yes, yes, yes.
Okay. What about cost effectiveness?
Yes,
Right?
yes.
This is helpful. I am synthesizing carbon dot from hydrothermal through hydrothermal synthesis, hydrothermal method. This only need stainless steel autoclave. This is a one-step synthesis method. Hello.
Okay, fine, fine. So, is there any other questions? Okay, then. And thank you, Anurus. We can go for the next presenter. Let me invite Atulya Jaykumar, Government Victoria College, Palakkad, on the topic of electro-deposited and loaded type.
Hello, sir. Hello, sir.
Yes, you are audible. Share.
Okay, ma'am. Is it visible, ma'am?
Yes, it is visible. Please put it in slideshow mode.
Okay, ma'am. Good evening to one and all present here. I am Atulya Jaykumar, PhD student at Department of Physics, Government Victoria College, Palakkad. First of all, I would like to thank the Organization Committee of ICN 2022 for giving me this opportunity. And now I'm going to present the report of my work, Electrodeposited CZTS loaded titanium nanotubes for photocatalytic water splitting. First, copper zinc tin sulfide is a promising semiconductor and it is a good candidate to be used as an absorber layer in thin film solar cells. Similarly, titania, that is titanium dioxide, TiO2, is widely investigated for photocatalytic water splitting. But one of the main drawbacks of TiO2 as a photocatalyst is its wide band gap and thereby its inability to utilize the visible light of solar spectra. So in this work, we made use of CZTS as a buffer layer in order to reduce the effective band gap of TiO2. So as a first step, we prepared the titanium nanotubes by anodization of the titanium foil, and it was done in a 2-electrode system with titanium foil as the anode and platinum mesh as the cathode. And the electrolyte we used for this purpose was ethylene glycol, which was containing 0.3 weight percentage ammonium fluoride and 0.3 volume percentage water. And initially it was washed. The titanium foil was washed in deionized water, and it was sonicated in isopropanol and acetone, and it was dried. Then the anodization was carried out at 55 volt for 4 hours. After that, it was sonicated in isopropanol for 5 minutes and dried in air. Then it was annealed at 500 degrees Celsius for 2 hours in air. The next step was deposition of CZTS thin films, and it was carried out by electrode deposition. In electrode deposition, we used a potentiostat, and we have converted an ordinary DC power supply into a potentiostat in our laboratory. And it is a conventional 3-electrode potentiostatic mode in which we used silver bar silver chloride standard electrode as the reference electrode, platinum wire as the counter electrode, and TNT coated titanium foil as the working electrode. And the electrolyte we used was an aqueous solution containing copper sulfate, zinc sulfate, tin chloride, and sodium thiosulfate. And we used trisodium citrate as the complexing agent and tartaric acid in order to maintain the pH of the electrolyte. And the deposition was carried out at 2.5 volt for 5 minutes. After that, it was rinsed with deionized water and it was dried in air. Then it was annealed at 200 degrees Celsius for an hour. The pictures of the experimental setup and its schematic is shown here. Now going to characterizations, the FSM images of both bare TNT as well as the CZTS deposited TNT is shown here. Both views, that is the view from the surface as well as the side view, is shown here. And from the FSM images, we found out that the average tube diameter was 86 nanometer, and the deposited CZTS layer has a fibrous structure, as well as the approximate length of the TNT was 12.6 microns. After that, we set up a photoelectrochemical cell using a cubical quartz vessel with titanium foil coated with CZTS, sensitized titanium nanotubes as the anode, platinum mesh as the cathode, and aqueous solution of sodium sulfate as the electrolyte. After that, the anode was irradiated with a blue light of wavelength 430 nanometer at the power 50 milliwatt. Then the photocurrents were measured using Keithley SMU 2450 in our laboratory, which was set in the ammeter mode. And we found out the current density to be 0.1 milliampere per centimeter square, and the instant photon to current conversion efficiency was calculated to be 1.1%. And the energy level diagram showing the photo generation of electron hole pair and transport of electron and holes across the CZTS and TNT junction is shown here, as well as the schematic of the anode and photoelectrochemical cell is shown. So from our work, the efficiency of the photoelectrochemical cell reported is not so very high, but we can conclude that the photocurrent clearly indicates there's a possibility for this process, and by improving the interface properties and by reducing the recombination of the photogenerated carriers, we'll be able to get better values and more efficient hydrogen generation. Okay, these are my references. Thank you.
Is there any questions? If there are no more questions, let's move on. Next, I invite Mr. Theodore, Faculty of Chemical Engineering and Environmental Protection, Technical University of Romania, to present on the topic hybrid plasmonic catalysis using heterostructures of metal nanoparticles and layered double hydroxide.
Hello, I am present.
Please share your PPT.
So it is visible.
Yes, it is visible.
Okay, so good afternoon to everyone. I present the hybrid plasmonic catalysis using heterostructures of metal nanoparticles and layered double hydroxide. This complex field of nanoscaled structured materials present an important direction of research materialized mainly around layered double hydroxide materials due to the nature, structure, and the specific properties characteristic of the materials. Layered double hydroxide are a porous layers matrix, also known as anionic clays with a high absorption capacity of anions that have attracted attention in recent years due to their potential to be used in applications such as catalysis, photocatalysis, nanotechnology, biotechnology, biomedicine, and others. In figure 1, we have a schematic representation of the structure of layered double hydroxides. Materials and methods. We synthesize magnesium to aluminum LDH. Was calcinated at 550 degrees for 4 hours to the mix, and the mix oxide results were dispersed in 100 milliliter of silver sulfate solution under intense simmering at room temperature for 2 hours. After we separate the product by centrifugation, wash and dry and at 40 degrees overnight. Xrd analysis, which denote the reconstruction of the initial layer double hydroxide with a minor loss of crystallinity, and the formation of the new phases of silver nanoparticle and silver oxide. Testing as synthesized samples in photodegradation using a solar lamp of paranitrophenol. In figure 3, TEM analysis, we can see the silver nanoparticle deposed on the surface of the LDH layers. Raman data correlate with the results provided by Visible Spectra, confirm the coexistence of carbonate sulfate anions in the LDH galleries for sample reconstructed in silver sulfate silver aqueous solution. And in figure 5, degradation of paranitrophenol under solar light radiation by silver LDH. We synthesize silver nanoparticle with different percentage intercalated into LDH surface layers. 3% silver on magnesium aluminum 3-1 showed a very good photocatalytic activity with complete degradation of paranitrophenol in 180 minutes. 3% silver magnesium aluminum 2-1, 7% silver magnesium aluminum 2-1, and silver percentage silver 7% silver magnesium aluminum 3-1 showed good photocatalytic activity with a complete degradation of paranitrophenol slower in 270 around 300 minutes, while 20% silver zinc aluminum 1 had an even slower activity, and 7% silver zinc aluminum 1 with a very low activity. In the figure 6, this graph better highlights the time the degradation was performed. In figure 7, degradation of paranitrophenol under solar light using a cutoff filter. In this photocatalytic test, 7% silver zinc aluminum 1 better activity in paranitrophenol degradation was when the test was performed without filter, compared to 3% silver zinc aluminum QR, where degradation without filter was in 180 minutes and with filter in 240 minutes. Reduction paranitrophenol using silver LDH, silver nanoparticle. Following the test, the compound 7% silver zinc aluminum 1 had a very good reduction of paranitrophenol with a reduction in less than 1 minute. The compound 20% silver zinc iron aluminum 2-1 and 20% silver zinc aluminum 2-1 had a good reduction in 9 minutes. The rest of compounds had a slow or even very slow reduction. And conclusion, layer double hydroxide materials are a large group of nanostructured materials that belong to the class of anionic clays, different nanoparticles of transitive or noble metals, nanoparticles of noble metals, metal oxide, as well as biomolecules can be incorporated on the surface of layer double hydroxide to offer the possibility to create efficient catalytic or and non-catalytic nanoclays in different fields. By calcination of LDH at 550 degrees, we obtained metal mixed oxide. We synthesize layer double hydroxide by direct precipitation and their heterostructures by reconstruction method, exploiting their property, namely memory effect. Using the manifestation of the structure memory effect of LDH and anionic aqueous solution, we obtain silver nanoparticle dispersed on the surface of the LDH clays. The results demonstrate that the clay catalysts with a different concentration of silver are good in photodegradation of paranitrophenol. And that's it. Thank you for your attention.
Okay, the session is open for questions.
So it is okay.
Yes, Theodore.
Okay, so thank you and good luck to everyone.
Thank you. So thank you, Theodore. We'll move on to the next presenter.
Next, we can move to next presenter, Miss Charu from Academy of.
Yes, I'm here. Can you hear me?
Yes. Please share your PPT.
Yeah. Is my screen visible? Hello?
No, it's not visible. Yeah, it is coming. It's fine.
So, may I start?
Yes, you can.
Good evening to everyone. I am Charu from ACSR, working at CSR NERI under the supervision of Dr. Sukhdev Pal. So I had to deliver a poster on heterolayered nanostructures for removal of physicochemically diversified contaminants based on dual modality adsorption photocatalysis. It is extremely challenging to effectively remove multiple coexisting contaminants of varying physiochemical characteristics using a single material. So, intrigued by this challenge, we synthesize a multifunctional self-generating material by combining two different nanosheets of different chemical and physical properties with an appropriate semiconductor for the effective charge separation. And for this purpose, we made a composite material consisting of TiO2 as a bench photocatalyst, and a positively charged layer, nano layer, that is LDH, layer hydroxide, double layer hydroxide, and then both the materials were then went for hydrothermal synthesis. After that, a brucite-like layered structure was prepared, and further the prepared structure was exfoliated. Secondly, a defect-rich MOS2 layer was prepared hydrothermally, and a trigonal prismatic structure was prepared. Due to the hydrothermal treatment, interlayer spacing between the layers were increased and defects were created, as a result exposing inaccessible sulfur-rich site on the basal plane of the structures. Then the prepared structure was further exfoliated. The exfoliated structures, nanolayers, were further combined using electrostatically derived self-assembly reaction, and as a result, TiO2 incorporated LDH MOS2 structure was made. These are the results which were obtained from the study. So these are the TEM and HR-TEM images of MOS2 and TiO2 incorporated LDH. The first image shows the wavelet structure of MOS2, and this image shows the interspacing which were created between the layers of MOS2 during hydrothermal reaction. And this particular image, it shows the defects which were created during the hydrothermal synthesis. This image shows the hexagonal structure of LDH and TiO2, which were dispersed on its surface uniformly. One thing we can note from here that after the incorporation of TiO2, the integrity of the LDH did not alter, and the TiO2, they were dispersed on the surface of LDH rather than in between the layers. By combining positively and negatively charged layer, we made a structure that is TiO2 incorporated LDH MOS2. As we can see here, this is the TEM image of the structure, which is shown in solid lines and dashed lines. So for the confirmation of the coexistence of constituting components in the prepared heterostructure, we went for HRD studies, and this particular figure shows the HRD pattern of synthesized material. So for MOS2, LDH, TiO2 incorporated LDH, and the heterostructure which was prepared using electrostatically driven self-assembly reaction. Further, the confirmation for the presence of Mg, Al, and Ti, Mo, and S was made using XPS spectra of orbitals. This particular image shows the two distinct doublets of 3D 3x2 and 3D 5x2, and particularly it shows the that the MO which was present in MOS2 was in +4 oxidation states, and similarly two doublets were prepared has been shown for S2P 1x2 and S2P 3x2. Further investigations for the prepared heterostructure was done for the removal of cationic and anionic dyes, that is rhodomine B and Congo red dye, under dark and light conditions. So this particular figure over here, it shows the reaction of RHB under dark conditions. So the peak of RHB at 572.5 5 nanometer get flattened in the presence of MOS2 being positively charged layer, whereas if we see in case of Congo red dye, the peak of Congo red, which is at 498 nanometer, get flattened in the presence of yeah ma'am, just in a sec, I'll conclude. In the presence of LDH and titanium incorporated LDH. So and similar results were obtained for the synthesized heterostructure, and these are the experimental conditions which were followed throughout the experimental process. So this schematic shows the illustration of ROS generation and the degradation mechanism of dyes. So the electrons which are generated in the valence band of the MOS2 get jump into the conduction band, and then which are transferred to the of the TiO2, and these further react with oxygen to form superoxide species. And meanwhile, the the holes which are generated in the valence band get transferred to the valence band of the MOS2 and form hydroxyl ion by combining with water. And this particular figure shows the removal efficiency metal ions in coexisting metal ion solution. So the prepared heterostructure was investigated in a coexisting solution, and the highest efficiency obtained for was 100%. And the further experiments were done for and Langmuir plot has been obtained, and and the value of R square was around 0.94. From this study, we can conclude that the obtained structure can display both adsorption and photocatalysis. Also, the obtained structure UV visible region photo activity, and it can rapidly remove both the dyes, that is RHB and Congo red, in 15 minutes, and the selected dyes
Miss
resulted in
Charu,
more than 80% removal.
can you conclude?
Yes, sir. So yeah, I'm about to conclude, sir.
Okay.
In the dark oils, in 95% eradication in the light. Also, which we can draw from this study is the synthesized material can be utilized for the removal of other pollutants like PPCPs and POPs, irrespective of their physical characteristics like charge, and considered as a suitable candidate for advanced material for water treatment. Thank you.
Okay, the session is open for questions.
If there are no more questions, we can go to next presentation. Miss Ilhan Khan.
Hello. Hello. Good evening. Am I audible?
Yes, you are audible. You are audible.
Am I audible?
You are audible. Please share your PPT.
Is it shared or not yet? The screen. Hello.
It's not visible.
It's not visible.
Not visible.
I can't share it. The option is not coming.
Okay, and then please send us the PPT. Then we can move to next presenter, and we will call you after that.
Okay.
Mr. Harshil Thakur. Harshil?
Yes, ma'am. I'm here.
Yeah, please present.
Okay, ma'am. Yes, ma'am. Is the screen visible?
Yes, it is visible. You can present now.
Okay. Yes. A very good evening to each and everyone present over here. I am Harshil Thakkar, working under the guidance of Dr. Sonal Thakur from the Department of Chemistry, the Maharaja Sayajirao University of Baroda. And today I am going to present a poster on construction of large 4 covalent organic frameworks and its fabrication on carbon nanotubes as high-performance adsorbents for organic dye removal. The model organic dyes that we have selected is malachite green, which is the cationic dye, and methyl orange, which is the anionic dye. So covalent organic frameworks are basically porous organic frameworks which are fully pre-designable based on topologically directed polymer growth in conjugation with the geometry matching between the monomers. These COFs that have been synthesized, they possess superior properties like ordered geometry, high porosity, high stability, and post-synthetic tunability in physical and chemical forms. Because of these superior properties they possess, they have found several applications in numerous fields, one of them being environmental remediation as an adsorbent. To further explore and enhance the adsorption properties of covalent organic frameworks, we have fabricated this COF onto CNT. So now let us come to the synthesis of COF and COF-CNT composite. So covalent organic framework was basically synthesized by reaction between the two monomers having C3V symmetry, that is melamine and barbituric acid, by solvothermal approach using DMSO as a solvent and glacial acetic acid as the catalyst. Further, we also fabricated this COF onto the CNT in 3 sequential steps. The first step being the carboxylation of the carbon nanotubes. The carbon nanotubes were carboxylated used by acid treatment. This carboxylated CNTs were then reacted with 4-hydroxybenzaldehyde via esterification reaction in the presence of DCC and DMAP to give us the functionalized CNTs. These functionalized CNTs then were reacted with melamine and barbituric acid in the similar manner to how COF was produced via
Hello.
solvothermal approach.
Hello. This
Hello.
Ethan Khan, can you please put off your mic? It is disturbing continuously.
Yes, can I continue
Yeah.
now? Yes. So this functionalized CNTs that were obtained after esterification were then reacted with melamine and barbituric acid via the same solvothermal approach to fabricate this COF onto the carbon nanotubes. These COF and these COF CNTs were then characterized using FTIR, NMR, powder XRD, BET, and FESEM. The FTIR over here distinctly shows the presence of secondary amine and imine linkages in the case of COF, and the presence of secondary amine and carbon oxygen stretching frequency for ester linkage, and carbonyl frequency again for ester linkage and imine linkage in COF CNT. Similar results confirming the graphs obtained from the FTIR were obtained in solid state NMR. We had to go for solid state NMR because the compounds being extremely stable, they are insoluble in most of the solvents. Next, coming to the powder XRD. The powder XRD shows a broad peak at 22 degrees, which is basically an indicative that the COF and COF CNT possess amorphous nature. The BET adsorption desorption graphs shows that the adsorption capacity of COF CNT is far more better compared to COF. The FESEM images that have been shown over here distinctly indicate the porous nature of COF, which helps in the dye encapsulation. So now coming on to the dye adsorption experiments. We had performed the dye adsorption experiments using malachite green as a cationic dye and methyl orange as an anionic dye with both COF and COF CNT individually. With COF, we had studied different parameters. We have increased the initial dye concentration, and upon the increase in initial dye concentration, the removal efficiency decreased. The graph over here distinctly shows the COF having more affinity towards cationic dye malachite green compared to that of methyl orange, primarily because of the electrostatic interactions between the electron-rich groups on COF and the cationic dye malachite green. We also studied the effect of adsorbent dosage, that is, by varying the COF amount, the adsorption capacities and the removal efficiencies also increased. Similar studies were also performed with COF CNTs, but the adsorption studies with COF CNTs indicated that the removal efficiencies are far more better for both anionic as well as cationic dyes compared to that of native COF. Further, we had plotted different adsorption isotherms, and amongst them, the adsorption studies best fits the Langmuir adsorption isotherm with the maximum adsorption capacities of being 555 and 217 milligram per gram for malachite green and methyl orange with COF, whereas for COF CNTs, the adsorption capacities were 588 and 238 milligram per gram. Further, the kinetic studies were also performed, which showed that it follows pseudo second order kinetics. Finally, the regeneration and reusability studies were also performed, which indicated that COF and COF CNTs can show a removal efficiency of greater than 80% even after 10 successive cycles. So coming on to the conclusion, from this work, we conclude that we have synthesized covalent organic framework based on barbituric acid for the first time and also fabricated the COF onto CNT to form its composite, and we have successfully characterized it with several techniques. The adsorption isotherms are also plotted, which depicts that the adsorption is monolayer, follows Langmuir adsorption model, with the adsorption capacities being quite high. And these adsorption capacities which we have found is exceptionally high compared to the previously reported adsorbents, which show the adsorption capacities less than or nearly equal to 200 milligrams per gram. The regeneration and reusability studies indicated that we can use COF and its composite for 10 successive cycles with greater than 80% removal efficiencies, showing its practical applicability. And from these studies, we also conclude that COF can have practical applications in dye separation because it has more affinity towards cationic dye.
Can you conclude?
Yes, sir. Whereas COF CNT, as it is having more affinity towards both the dyes, it can help in efficient simultaneous dye removal in binary mixtures. Finally, I would like to thank the ICN organizers for giving me this opportunity, Gujkos Gandhinagar for financial assistance, Raman Research Institute for powder Xrd, and SAF Bombay for FESEM and 13C solid state NMR analysis. Thank you.
Thank you, Harshil.
Yes, ma'am.
Is there any questions?
Thank you, ma'am.
Is there any questions?
What is the advantage of making this composite of CNT and COF?
The advantage is that COF specifically interacts more with the cationic dye because of the electron-rich functionalities present on COF, and it has less affinity towards methyl orange, which is the anionic dye. But if we want to simultaneously remove both the dye, which is basically of practical use in environmental applications, for that we have deliberately fabricated the COF onto the composite so that the adsorption capacities also increase and there is affinity towards the anionic dyes as well.
Okay, thank you.
Yes, ma'am.
Okay, moving on to the next one. I invite Manish Yadav, School of Material Science and Technology, IIT, BHU Varanasi, to have the talk on structure and magnetic properties, along with bipolar magnetization switching in nanoparticles of cerium ion.
Hello. Hello. Am I audible?
Yes, you are.
Sharing option are not available here. Can you please share my PPT?
Okay, please send us your PPT.
Actually, I have sent 2 hours ago.
Okay, we will call you as next presenter. Now, Miss Ilhan Khan, we will share your PPT. Manish Yadav, we will present your PPT by next.
Okay.
Hello, am I audible to you?
Yes, you're audible. You can start now.
Okay. Good evening, everyone. I am myself Ilhan Khan, and my topic for today's presentation is the evaluation of the quinseed anti-cancer activity and its nanoformulation on the HER2 cancer cell line. So I have prepared the extract of the quinseed that is commonly known as the bihi dana in India and also known as a golden apple. I have prepared its extract using Soxhlet apparatus and in a methanol solvent. So this extract has been used and incorporated in the nanoemulsion form. We have determined the co-surfactants and water and the ratio of that extract by using the aqueous titration method that has been determined by the, please change the PPT to next slide. So I have used a pseudo-turning diagram to determine the ratios of different surfactants and the water percentage that we have used to prepare the stable nano formulation here. The formulation that we have prepared is further characterized for the size and morphology. And the nanoemulsion that we have used here has a nanometer size of 190 nanometer with a PDI of 0.291. We have further characterized the presence of the extract in our nanocapsulation is determined by using the FTI analysis. And we have seen that the CH and CO stretch is found similar in the same absorbent range in both the FTIR analysis. And further, for the morphology characterization and size determination, we have done the TEM analysis on the scale of 200 nanometers, and we have seen a circular and oval-shaped morphology of a nanoemulsion. For the in vitro and drug release, we have calculated the sustainable release, which has been shown up around 73% of drug release at the 8-hour of interval. Please go to the next slide. After characterization of a nanoemulsion and extract, we have studied its effect on the hepatocellular carcinoma cell lines. First, in the first study, we have checked on the cell line morphology, how it's affecting. We can see in all the time interval of 24 and 40 hours that the cell number are decreasing on a dose-dependent manner and as we increasing the time period. Using the MTT assay, we have determined the cell viability over the time period and also calculated its IC50 value. From this MTT analysis, we have seen that our nanoemulsion showing quite significant results in comparison to the extract. Further, we have also checked the cell proliferation using the colony forming assay for both the nanoemulsion and the extract. And we have seen that over time period of 24 and 48 hours after the treatment, the cells committee is not growing colonies, quite greatly has been inhibited. Further, for the anti-cancer potential, we have assessed the nanoemulsion and extract using the ROS and for the chromatin or DNA defragmentation methods. Please go to the next slide. And we have seen that in comparison to the extract, our nanoemulsion is showing a greater frequency of ROS scavenging activity, and similar for the DAPI, the DNA and chromatin condensation are greatly visible in the nanoemulsion compared to the control and extract treatment. Further, we have studied the apoptotic potential of a extract and nanoemulsion using the cell cycle and apoptosis facts analysis, in which we have seen the later and earlier apoptosis phase showing the higher percentage compared to the necrosis factor. And so we can, by the cell cycle analysis, we can conclude that our cell is arresting due to the apoptosis induced. And we can see that our cell is arresting in the G1 phase in both the extract and nanoemulsion. Further, we also calculated the mean frequency intensity of the ROS scavenging antioxidant property. And here also we have seen that our nanoemulsion is showing better result compared to extract and then the control. We also estimated the membrane potential analysis, which is another property of apoptosis determination. And we have seen here also that our cells have showing the shift in the membrane potential, which represents the apoptosis of the cells due to the treatments of a various concentration of extract and NU. So this whole study of mine is actually determining how these nano health formulation, herbal formulation is actually affecting on the HER2 cellulomas and what is the impact of it on various cancer cell lines. Thank you.
Is there any questions? Is there no more questions? We'll move on. There is an announcement.
Okay, thank you.
From P8 P28 to P36, kindly move on to Hall 1. From P28 to P36, please check chat box also. Hall 1. Moving on to the next. The next presenter is Manish Yadav. Okay, we present now.
Hello. Hello.
Yes, yes, we can hear you.
Okay, am I audible? Hello.
We can hear you. Manish, you
Okay.
can start now.
So I am going to start. So myself Manish Yadav, research scholar from the School of Materials Science, IIT BHU. I'm going to present here structural and magnetic properties along with bipolar magnetization switching and nanoparticle of iron dot cerium chromide. So this cerium chromide generally had the orthorhombic crystalline structure and it is stable up to 400 degrees C. It is in semiconducting in nature and its magnetic background is antiferromantic. And this cerium chromide possesses some unusual magnetic properties such as magnetization, reversal, magnetic compensation, and spin reorientation, which makes these materials a potential candidate for magnetic memory and spin resolving and spintronic devices. And here our objective is to study the structural and magnetic to study the structural and magnetic transition of these nanoparticles and to explore its potential application in magnetic memory. So these materials are synthesized through cost-effective glass and nitrate solution combustion method, in which we taken the precursor in a stoichiometric ratio, mix this in 30 ml water and steered for 1 hour at 18 degrees C. After the formation of gel, the temperature was increased to 350 for the combustion. When the combustion takes place, we found the fluffy cerium chloride nanoparticle, which is grinded and used for the characterization. Please move on next slide. So structural analysis of these materials is done through the Xrd, which shows the formation of pure orthorhombic cerium chloride nanoparticle, and which is further confirmed through the ritual refinement. And the structural parameters are tabulated here, which shows with the doping of iron, the lattice parameter as well as the volume is increased, while as the super exchange angle is decreased. Further, these materials are characterized microstructure history done through the same item, which shows the agglomerated nanoparticle, the formation of agglomerated nanoparticles, and these material, these particle shape are slightly deviated from spherical shape. Please move on next slide. Further, the magnetic study of this material were done through the magnetic property measurement system, in which for pure there is magnetization versus temperature plot are shown for x is equal to 0, which is pure cerium chromite material, which shows the Neal transition temperature at 260 K and the compensation temperature at 61 K, while TSR at 15 K. The magnetization reversal of these material can be understood on the basis of three magnetic interaction, that is cerium-cerium interaction, cerium-chromium interaction, and chromium-chromium interaction. The magnetization reversal mainly due to the cerium and chromium interaction, which can be understood by a schematic diagram, are shown to the right of this magnetization versus temperature plot, where when that we cool down the material below that below the Neal transition temperature, the materials aligned chromium aligns to the applied field direction, and it induces the internal magnetic field, which try to align the cerium in the opposite to the applied field direction, that results in the magnetic compensation. Further, with doping the 5% iron, a new magnetic transition is appear at around 300 K. With the increase in compensation temperature and TSR 2 times, which is found at pure cerium chromite. Further, with the doping, the negative magnetization or dies out, and the Neal transition temperature due to the chromium and iron interaction is increases up to 380 Kelvin. Since we are interested in the magnetization compensation in negative magnetization, we explored these material pure and 5% doped cerium chromite for the magnetization switching. In this switching we switches the magnetization to the low to the high field. When we field cooled the material in the low field, we found a negative magnetization. Further increasing the high field, it shows the positive magnetization. These negative to positive switching of the magnetization can be understood on the basis of the movement of cerium movement in the superposition of internal and external field. So here the conclusion is that these material can be prepared by one step by glycine nitrate solution combustion method, and the average particle size of all the composition are less than 80 nanometer, while these material 5% doping 5% doping in cerium chromite increases the composition temperature twofold, 2 times the pure one. And these stable bipolar switching magnetization makes these cerium chromite nanoparticle imminent material for mounting memory application. So here is the references we have used, and here our published article are also given in references. And so I would like to acknowledge the CSIR for financial support, and CIF IIT for providing that time and magnetization measurement facility.
Is there any questions? Okay, we can move on to the next presenter, Miss Manisha.
Okay, thank you.
Miss Manisha from Department of Chemistry, University College of Science. Hello, Manisha.
Okay, we can move on to next presenter, Miss Nina Mol John, School of Chemical Science, Mahatma Gandhi University. Miss Nina Mol.
Yes.
You can start your presentation.
Okay. It is visible.
It is visible. Yes, it is visible.
Okay. My presentation in Inomer is due to characteristic of photo degradation of green block. This is effective for degradation of organic pollutant. Most of the non-potent catalysts conducting in nature. Compounds are commonly used for photocatalysis. Simple mechanism for photocatalysis means light is radiated from the surface of the semiconducting material. Then the valence transfer to the photogenic electrons and holes are used for producing reactive oxides, species like hydroxide radical and superoxide radical. These hydroxide and superoxide for hazardous material. Electron used as an the degradation and dark speed. And we modify to enhance the activity of silver sulfate. We dop this material with the sulfur doped graphene oxide. Sulfur doped graphene material, conjugated aromatic ring, enhanced conductivity of SO sheet, improved charge separation, and improved ability of objective of fiber. Synthesis of extraneous nanocomposite, characterization of nanocomposite, optimization of the composite, and investigation of the photo.
We think Nina Mol have some network issues. So we are moving to next. Ms. Sadia Samreen, Natural Products Laboratory, Department of Bioengineering, Integral University, Lucknow, India. Ms.
Yes,
Sadia.
ma'am. Am I audible? Yes.
Yeah, you are audible.
Hello.
Yeah, you are
Okay,
audible.
ma'am.
Yes, it is visible.
Everyone. Dr. Xrd Results at Department of Bioengineering, Integral University, Lucknow.
Hello, Sadia. You are not audible.
Application and in vitro anti-cancer evaluation of Cerium inhibitors extract load.
Hello, Sadia. Yes. Now it's
Am I audible now?
it's fine.
Okay. alone, 33 herbal formulations are available, in which chicory is the main constituent of. So we have taken two phases, which is oil phase and aqueous. Is in oil phase, GMS that is cleared by mixing DI and polyethylene glycol. And aqueous phase was kept under probe sonicator, and oil phase was slowly dispersed in it. And after 10 minutes, temperature was allowed to reduce at 4 degrees centigrade, and sonication. Nanoparticles were achieved, and 9 nanometer, and diffraction and morphology of the developed nanoformulation, and FTI analysis for the functional group and the nature of the sample, and drug loading and nurse efficiency was also measured, and it was found that 85% was the drug efficiency. So for the in vitro part, we have used human liver cancer cell line, that is HG2 cell line. So first, this assay was done was MTD assay, in which we determined the incubation time, that is 24 and 48 and 74 hours, for which concentration 50% of the cells were killed, and at what dose. So IC50 determines this. So the IC50 value was found to be 59 microgram per ml, and at this stage, by using microscope, whether the cell is killed. So after that, we that the ROS level is different in the different stages. This is no ROS is generated in this, and on the cancer cell, the ROS is increasing in the different stages. So after that, we use station. We use DAPI analysis, DAPI, which is and it binds to the A-rich region of the double condensation occurs or fragmentation occurs. And after that, the colony forming assay was also performed. See the ability of the cells to grow colonies of the cancer. It has a enough number of colonies, and after treatment it gets decreased. Cell line, normal liver cell line, that is, we have use FACS analysis by using an Xrd kit using PII and the micro. So we can see that the early and late process is occurring, and second was the ICN value. And by using JC1 dye, and we can see that the potential is shifting towards green, that is, membrane potential is decreasing. And in the third one, we can see the cell analysis, and we can clearly see that it is arresting in the G1 to S phase. G1 phase, and second one is the dash hash line in G1S phase. tract was shown to possess hepatoprotective and anti-cancer potential, and in vitro assays shows time and proliferation and increased cell death and RML against HG2 cell line. So overall, it can be concluded the chicory extract-based nanoformulation could be effective against liver cancer and could be used in a drug delivery. Thank you.
Thank you, Sadia. Is there any questions? If there are no more questions, we can move on to next presentation. Ms. Harsha Haridas, Department.
Okay, thank you, ma'am.
Harsha Haridas, Department of Physics, National Institute of Technology.
Ma'am, could you please share my PPT? There is no share option here. I have already sent you.
Okay. Okay. We will share. Meanwhile, if Nina Mol is present, we can. Hello, Nina Mol.
Okay. My PPT is visible.
Yes, it is visible.
So my title of my presentation is a novel SGU reduced catalyst for photodegradation of methylene blue. Photocatalysis is an efficient method for the degradation of organic pollutant. Catalysts are semiconducting in nature. Metal oxide, metal halides, and metal sulfates are well known. Silver-based compounds are commonly used for photocatalysis. This is a simple mechanism of photocatalysis. When its light is radiated on the surface of the material, electrons are transferred to the valence band to the conduction band. The photogenerated electrons are hot cell capable for producing reactive oxygen species like superoxide radical, hydroxyl radical, etc. In this work, we mainly focused on silver sulfide material. It is a second for sulfur doped GO is used as a co-catalyst for silver sulfide, which possesses material and enhance the conductivity of GO sheet, improves charge separation, improves the stability of photocatalytic nanomaterial element. Am I audible? Hello?
Hello, Ninamol. Hello.
Am I audible?
Yeah, you're audible, but some. Okay, it's fine. Now you're audible.
My PPT is visible.
No, actually, it's not.
It is visible.
It is not.
But actually, I'm more.
Okay, now it is visible. Now it is visible.
Okay. So the objective of my work is synthesis of SGU EDTS nanocomposite, characterization of synthesized nanocomposite, optimization of the catalyst, and investigation of degradation of methylene blue in aqueous solution. The synthesis of SGU EDTS is by simple one-pot microwave method, and this we can see that the silver sulfate particle is embedded on the surface of the material. Result and discussion: the synthesized material is characterized using different characterization technique. First one is Xrd spectra. From Xrd spectra, we can clearly see that 5% modified SGO modified AG2S was found to be exact replica of AG2S. The diffraction peaks were assigned to be monoclinic phase with a lattice constant A is equal to 4.2. B is equal to 6.9 and C is equal to 7.8. From FTIR spectra, the presence of, we can understand the presence of functional group. The FTIR spectrum of SGO shows peak at 1220 and 1500 corresponding to CS bond. And pure AG2S shows peak at 1135 and 158 due to the presence of AGS bond. Then the third one is the PL spectra. From PL spectra, we can understand the combination of GL. From the PL intensity is very low for SGO, AG2S, and AG2S. That means AG2S has lower recombination rate than the pure AG2S. Then third one is a SEM and GEM characterization technique due to understand the surface morphology of material. From SEM analysis, the semi-images of pure AG2S displays the presence of cluster-like structure. Upon modification with a 5% SGO, the morphology was observed to change. And the silver sulfate particle is embedded on the surface of the SGO sheet. The SAED pattern gives an idea about the formation of SGO and AG2S. The one or multi-layer of SGO sheet formation of nanocomposite and spots corresponding to AG2S particles, and EDX analysis gives a confirmation of the presence of elements present in our nanocomposite. Am I audible?
Yes.
Okay. Then the UV visible spectra. UV visible spectra give an idea about the absorption capacity of AG2S and 5% AG2S material. From this UV spectra, we can clearly understand 5% of SGU AG2S have higher absorption capacity than AG2S. From this plot, from this data, we can calculate the band gap of our material. The 5% of SGU AG2S has the band gap at 1.16 and AG2S has 1.50 electron. Then application. The main application of this material is degradation of methylene blue. From this UV spectra, we can clearly understand that 5% of SGU AG2S has degrade around 71.90% of methylene blue within 120 minutes with a rate constant 1.07 into 10 raised to minus 2. Scavenger study, EDTA benzoquinone are used as scavenger for the purpose. From the another important result of my study is the presence of EDTA. The catalytic activity of SGO was enhanced because it on a more electron to our system that will enhance the activity of our material. And the this is a simple schematic representation of our system. The light is irradiated on the surface of the AG2S. The electrons in the valence band transferred to the conduction band, and this photogenerated electron transferred to the SGO sheet. That will help to O2 into superoxide radical and water into hydroxyl radical. And finally, the O2 dot H plus and electrons are capable to degrade pollutant into less hazardous material. Conclusion and outlook: the novel SGO AG2S photocatalyst was successfully synthesized by one-pot microwave assisted method. The synthesized catalyst was characterized by different characterization technique. Around 71.9% of methylene blue was degraded by 5% of SGU editors. In presence of EDTA, 85.21% of methylene was degraded. 5% of SGU editors combination with the sacrificial agent EDTA is a promising catalyst for the efficient degradation in dyes in water. The catalyst can be applied to other pollutants like pesticide. The activity can be enhanced by modifying with the transition metals or lanthanides. Thank you.
Okay, thank you, Nina. The session is open for question now. Okay, is there no more question? We can move on to the next participant. Thank you, Nina.
Thank you.
So, Harsha Hadas, we received your PPT. We will share it now. You can present. Okay.
Okay. Am I audible?
Yes, yes, you're audible.
Okay. Good evening all, myself Harsha Haridas.
Harsha, you can start now.
Good evening all, myself Harsha Haridas. I'm a PhD student doing my PhD under the guidance of Dr. Gautam Kumar Chandra and Dr. M.K. Ravi Verma of Department of Physics, NIT Calicut, Kerala. My research topic is green synthesis of eco-friendly silver nanoparticle using coffee arabica leaf extract and development of a cost-effective biosensor for cysteine. We know green chemistry approaches play a vital role to implement sustainable and environmental friendly pathways to produce desirable modes with unwanted products having minimum toxicity and side effects. So we have chosen coffee arabica leaf because we know coffee is a well-known common beverage familiar to all over the world. Even though lots of research work have been done related to coffee bean and all, the utilization of coffee leaves are very rare. Even though coffee arabica leaf contain lots of phytochemicals like flavonoids, caffeic acids, chlorogenic acids, their contribution towards the material science is not done so far. So here we can see the methods I have chosen. It can be included in three, that means it is imparted in 3 steps: extraction, synthesis, and biosensing. The extract of my the coffee leaf extract is prepared by washing the fresh leaf, and after washing let it keep for somewhat dry and make it to small pieces and boil it in distilled water at 100 degrees Celsius for 5 minutes and let it to filter using waterman filter paper and keep it cool to room temperature. We have used 1:5 ratio for synthesis of green reduced silver nanoparticle. Within 5 to 10 minutes, we can see the color change from pale yellow to brown color as the confirmation for CAE AG nanoparticles. Kindly move on to the next slide. We have done the UV characterization for the leaf extract itself. From the figure 1, we have confirmed the presence of major phytochemicals like caffeine and chlorogenic acid, and we have we proposed a probable mechanism that the electronegative oxygen contained in the caffeine and CGA is attaching on the surface of Ag, and it is parting in the reduction of Ag ions to Ag nanoparticle. Then after that, we got the beautiful surface plasmon resonance peak of AgNO3, and we have tried for different concentration of that leaf extract, and we got the intensity of the corresponding CAE Ag nanoparticle is increasing as we have increased the concentration of leaf extract, indicating the large number of Ag nanoparticles are formed. And for the functional group study, we have undergone FTIR and Raman spectroscopic studies. From FTIR ATR spectra, we can see the alkaloids, carboxylic acids, presence of alkaloids, carboxylic acid, as well as hydroxyl groups present in the leaf extract and their contribution towards the reduction of Ag ions. We can see the change in the intensity corresponding to OH hydroxyl groups towards the 3306 centimeter inverse wave number, as well as we can see the enhanced carbonyl peak intensity at 1640 centimeter, which indicate the mainly the carbonyl as well as the hydroxyl part of the coffee leaf is if coffee leaf is related to the reduction mechanism for the silver ions. And actually the Raman spectroscopic based on the study are very less. Based on the studies are very less. So we have conducted Raman spectroscopic study for our leaf extract as well as our prepared Ag nanoparticle. And from the spectra of figure number 4, we can confirm, we have confirmed the presence of AgO bond in the region of 230 centimeter inverse, which is the very good confirmation of the formation of Ag nanoparticle using hydroxyl group of phytochemicals present in the coffee arabica leaf extract. Further, we have turned to the application mode of our green synthesized Ag nanoparticle. We have applied it towards the sensing application. First, we have done selectivity and then sensitivity studies. We've taken around 9 different amino acids out of it and undergone UV visible spectral analysis, in which only 16 among 9 different amino acids, only 16 show a drastic deviation in the LSPR band of silver nanoparticle, as well as its intensity get reduced drastically. From this, we have concluded that a major chemical reaction have been happened in between silver nanoparticle and cysteine. So this LSPR based sensing method can be utilized for sensing application for cysteine using our green synthesized silver nanoparticle. From the inset of the figure number 5, we are showing the colors of corresponding samples. From this, we can see that only the sample containing cysteine shows the color change, which is a colorimetric response towards the sensing of cysteine within 5 minutes, as well as we gone for different dilution of cysteine in our CAE Ag nanoparticle, in which as we have increased the concentration of cysteine, the LSPR band of Ag nanoparticle goes on changing drastically, which indicates the adsorption of cysteine on a silver nanoparticle's surface. Kindly move on to next page. Further, we have gone for Raman spectroscopic studies of pure cysteine, as well as we have added cysteine to our synthesized CAE Ag nanoparticle. Here also we can see that in the case of pure cysteine, actually there is a SH bond, thiol group bond is present in the 2550 centimeter inverse range. But for the case of silver, after adding the cysteine to our silver nanoparticle, it is completely vanished. We can conclude it from this spectral results such that the reaction between silver nanoparticle and cysteine is done by the rupturing or distortion of the thiol group present in the cysteine, and it is formed with it is connected with the sulfur part of the cysteine is connected to silver nanoparticle and formed silver that means metal sulfur bonds are formed in the range of 480 as well as in the 230 centimeter inverse. It can be visible from Raman spectra itself. So we have again confirmed the sensing of silver cysteine molecules using our green synthesized silver nanoparticle, and then we have gone for the for finding the LOD using our green synthesized silver nanoparticle using Raman spectra. We undergone around 0.1 nanometer nanomolar concentration for cysteine, and we have detected even lower level detection can be possible. We have concluded that even in the lower level detection can also be possible using our green synthesized silver nanoparticle. So my conclusions are, we have fabricated a highly stable green reduced silver nanoparticle having 27 nanometer size using coffee arabica leaf for the first time, and the involvement of alkaloid, caffeines, CGA, and other phytochemicals in the formation of silver nanoparticle as reducing and stabilizing agent is studied from Raman, FTIR, UV visible studies, and UV visible studies.
Hello, Harsha. Please conclude.
Okay. All over, we can see that our green synthesized silver nanoparticle from coffee arabica leaf can be a better choice over environmental friendly biosensor towards amino acid cysteine. I'm greatly thankful to the authorities of ICN 22. Thank you.
Is there any questions? If there are no more questions, moving on to the next. I invite Ms. Sinisa for the poster presentation. Sinisa, can you hear me?
I'm sorry, I didn't hear that. Did you call me?
Yes, you can. Yes, you can present now.
Okay. Do you see my presentation?
No, we can't.
Just a second. Just a second. Okay, do you see now?
No. Yeah, it's coming.
Just a second. Now? Do you see now?
Yes, can you please make it in the full screen?
Okay.
No, it has stopped presenting. Can you present once again?
Just a second.
Please press.
Okay, do you see now?
No, we can't. While you're presenting, please select the entire screen option.
Yes, just a second.
Yes, we can see a.
Oh, sorry.
Yeah.
I will try again. Okay, entire screen and presentation. I hope you see now.
Yes, can you please make it the full screen? Slideshow mode.
Okay. So, do you see now full screen? No?
No, please click on slideshow mode.
No, I cannot. Do you see anything?
Then it's okay, you can continue.
Okay. So my name is Siniša Vučenović. I'm from Bosnia and Herzegovina, and my colleague Jovan Šetrović is from. I'm from University of Banja Luka, and my colleague Jovan Šetrović is from Academy of Sciences and Arts of our Republic of Srpska Academy in Bosnia and Herzegovina. So my work is about exciton states in molecular superlattices. So the structures which are named superlattices are made of ultra-thin films, which are mutually interconnected with regular and periodical pattern. So we did it in our theoretical research, and we have calculated the energy spectra of excitons. Superlattices could be created by some procedures such as molecular beam epitaxy or sputtering, etc. And but they are always made in such a way which modulate the motives, that is films. So of motives of alternating and periodically lined ultra-thin films. So the superlattices represent a new class in such a way, a new class of materials in which the newly formed potential is periodic one also, like in crystal structures. So here we can see a model of superlattices, one superlattice, which are made of Na layers of the type A, we call it A, constituent that is A film, and NB layers of the type B constituent that is a B film. Just a second. So we have formed standard Hamiltonian in the nearest neighbor approximation, which is showed here in this slide. And we have here parameters which are significant, which, for example, delta are energies of excitons on sites, while X are XA or XB are energies of exciton transfer between the same molecules along X, epsilon, or Z direction. And only with X we named this present exciton energy transfer between different molecules along Z direction. And of course we have here counters along all directions and in each motif or chain or film. So we have calculated dispersion law with green function method and their equivalent equation of motion for green function method. Why we choose green function method? That is because this method gives us directly dispersion law. So we are supposed to calculate all green function in one way, but we choose another way, so we cannot calculate particular green function because we just find the places or the spots where green functions tend to go to infinity. So this is circumstances that we have dispersion law directly. And of course, we have here a lot of huge complex calculation of all these commutators. And we performed also Fourier transformation. And after this Fourier transformation, we obtain equation of motion in this following form. So translational invariance in the superlattice is broken. In this case, we must perform partial spatial Fourier transformation because in the one direction we choose Z direction. Film are not infinite because in that direction they have only up to 20 layers. So that is the reason why we perform partial spatial Fourier transformation. And all these procedures are needed to obtain equation in K space or in space of momentum. So here it couldn't, in just 3 slides, we couldn't explain all these procedures in detail, but we have explained all in our paper and also in corresponding references. So if someone is interested in that, I will gladly share all that information. So to conclude, we have here calculated exciton energy spectra in superlattices, and we see that spectra split into a number of subbands. They have form of quasi-continuous subbranches separated from each other by forbidden zones. Also, the number of these subbranches depends on the number of film layers which are making one supercell. That is one motive of superlattice. And also we have see that ratio between energy transfer of excitons at the boundary and energy transfer within each film is significant. If that energy transfer between different films is smaller than energy transfer within each film, all subzones are located within the bulk boundaries. And the other solution there are formed localized or TAMS energy states appear. And when this energy transfer is equal, dispersion subbranches merge at the border of the first brilliant zone, and this occurring zero energy gap. So that will be all in my presentation. Is there any question?
Is there any questions?
Hello. Yeah, you can hear me.
Okay, if there are no more questions, we'll wind up today's session of second day of conference. Everyone is requested to join the final day of conference by 8:30 a.m. Thank you.
Thank you very much.